From the early moments of the Big Bang to the endless possibilities of future exploration, the universe has unfolded over billions of years, evolving from a singular point of unimaginable density to the vast cosmos we observe today. As scientists peer back in time, they unravel the mysteries of cosmic inflation, the formation of the first stars, and the development of galaxies in a dark, expanding universe. Looking forward, the trajectory of cosmic exploration is bound by neither time nor imagination. The next era of exploration may reveal the nature of dark matter and dark energy, test the boundaries of physics through the study of black holes, and potentially confirm the existence of life beyond Earth. Join us as we explore everything about the cosmos and what the future may hold. Stars begin their lives in vast clouds of dust and gas, known as molecular clouds. These clouds are primarily made of hydrogen, the most abundant element in the universe. Over time, certain regions within these clouds begin to collapse under their own gravity. This process can be triggered by various events, such as a nearby supernova or the collision of two clouds, which adds pressure and causes part of the cloud to contract. As the cloud collapses, it shrinks and heats up. This rising heat creates a core at the center of the collapsing region, called a protostar. Imagine the core like a growing ember in a fire. It becomes hotter and denser as more material from the surrounding cloud is pulled in by its gravitational pull. As the temperature continues to increase in the core, it eventually reaches a point where nuclear fusion can begin. During nuclear fusion, hydrogen atoms fuse together to form helium, releasing a tremendous amount of energy in the process. This energy stops the collapse of the protostar, and it becomes a main sequence star. At this point, the star achieves a delicate balance. The outward pressure from fusion energy counters the inward pull of gravity. Throughout their life, stars can go through various stages, burning hydrogen into heavier elements until they ultimately reach the end of their life cycle. Some may explode in a brilliant supernova, scattering their elements across space, while others may quietly fade away. This intricate dance of creation, transformation, and destruction highlights the ongoing cycle of stellar life that shapes the universe around us. The lifespan of a star is primarily determined by its mass, energy production, and the balance between gravity and internal pressure. A star's mass plays a crucial role. Massive stars burn their fuel much more quickly than smaller stars because their core temperatures are much higher. This rapid consumption of fuel means that a massive star might only shine for a few million years, while a smaller star, like our Sun, can linger for billions of years. Within a star, nuclear fusion occurs in its core, where hydrogen is transformed into helium, releasing vast amounts of energy in the process. The rate of this fusion depends on the star's temperature and pressure, which are influenced by its mass. Greater mass leads to higher temperature and pressure, which accelerates the fusion reactions. As a star ages, it exhausts its hydrogen fuel. The core contracts and heats up, causing the star to enter new stages of fusion. In larger stars, this can result in the fusion of heavier elements, leading to stages like red giants or supergiants. Eventually, when a star can no longer sustain fusion in its core, it will undergo dramatic changes and ultimately end its life in various spectacular ways, such as a supernova for the largest stars or a gentle shedding of outer layers for smaller ones. Additionally, a star's environment can influence its lifespan. Stars in dense clusters may interact with each other, potentially leading to accelerated evolution, while those in isolation can follow a more standard path based on their initial mass. Overall, the interplay of these factors creates a diverse tapestry of stellar lifetimes across the universe. Massive stars and smaller stars follow different paths in their life cycles, largely influenced by their initial size and mass. To understand this, let's first start with the stages these stars go through. Both types of stars begin their lives as clouds of gas and dust that collapse under gravity, forming a protostar. Once the temperature and pressure in their cores become high enough, nuclear fusion ignites, allowing the star to shine. For smaller stars, like our Sun, the nuclear fusion process primarily fuses hydrogen into helium for a considerable amount of time, often spanning billions of years. As they age, they will swell into a red giant, eventually shedding their outer layers to reveal a hot core known as a white dwarf, which will slowly cool down over time. On the other hand, massive stars initiate fusion much faster and burn through their fuel with incredible intensity. Instead of primarily fusing hydrogen into helium, they also undergo fusion processes that create heavier elements like carbon, oxygen, and eventually iron. This high-energy reaction causes massive stars to shine brightly, but only for a relatively short period, usually just a few million years. The end of a massive star's life cycle is dramatic. Once they exhaust their nuclear fuel, the core collapses under its own gravity and triggers a spectacular explosion known as a supernova. This explosion not only disperses heavy elements into space, but can also leave behind fascinating remnants like neutron stars or black holes, depending on how massive the original star was. While both massive and smaller stars share a common beginning, their life cycles diverge significantly due to their mass. Massive stars burn brightly and live fast, resulting in explosive endings, whereas smaller stars have long, stable lives that culminate quietly in the form of white dwarfs. This difference in fate not only shapes their own lives, but also influences the evolution of the universe itself as they contribute to the cosmic cycle of matter and energy. A supernova is a powerful and luminous explosion that marks the death of a star. This event is not just a single burst, it represents the dramatic conclusion of a star's life cycle. Stars are massive celestial bodies that produce energy through nuclear fusion, which is the process of fusing lighter elements into heavier ones. Throughout most of its life, a star maintains a balance between the outward pressure from the energy produced in its core and the inward pull of gravity. As a star exhausts its nuclear fuel, it can no longer sustain this balance. In smaller stars, such as our Sun, this leads to a process called a planetary nebula, where the outer layers are blown away gently. However, for more massive stars, the situation is more explosive. When these stars run out of fuel, their core collapses under the force of gravity, increasing in temperature and pressure. Once the core reaches an extreme density, it triggers a rapid series of reactions that lead to a catastrophic explosion. In this moment, the outer layers of the star are expelled at incredible speeds into space, creating a brilliant flash of light that can briefly outshine an entire galaxy. This explosion releases an enormous amount of energy and disperses elements throughout the universe, contributing to the cosmic material needed to form new stars, planets, and even life. Supernovae are categorized into different types based on their mechanisms. One type, known as a Type 1 supernova, occurs in binary star systems, where one star steals matter from a companion until it reaches a critical mass. Another type, known as a Type 2 supernova, happens when a massive star's core collapses after exhausting its nuclear fuel. These cosmic fireworks serve as both a spectacular end and a new beginning in the universe, reminding us of the dynamic and ever-evolving nature of space. The remnants of a supernova can become neutron stars or black holes, while the material ejected into space enriches the interstellar medium, paving the way for the next generation of stars to form. A supernova is one of the most dramatic events in the universe, occurring at the end of a massive star's life. When a star has exhausted its nuclear fuel, it can no longer support itself against gravitational collapse. This leads to a catastrophic explosion that releases an immense amount of energy. During this explosion, temperatures soar to billions of degrees, enough to trigger nuclear reactions that create new elements. As the star collapses, the intense heat and pressure allow lighter elements, such as hydrogen and helium, to fuse together into heavier elements. This fusion process builds up elements like carbon, nitrogen, and oxygen, much like how you might combine building blocks to create something larger. When the core of the star collapses and rebounds, it sends shock waves outward into the star's outer layers, igniting this fusion in an extraordinary way. These shock waves can create conditions conducive to the synthesis of even heavier elements, such as gold and uranium. During this extreme event, the rapid absorption of neutrons, tiny particles found in atomic nuclei, occurs as the explosion rips apart the star. This creates a process known as neutron capture, where atoms capture these neutrons and become unstable, eventually decaying into heavier elements. The result is a spectacular array of new elements, which are then scattered throughout space when the supernova blast ejects the star's outer layers. This debris enriches the surrounding universe with newly formed elements, providing the building blocks for future stars, planets, and even life. Essentially, each supernova not only reshapes the cosmos, but also plays an essential role in the creation of the elements we see around us today. Supernovas are among the universe's most powerful events, marking the end of a massive star's life. When a massive star exhausts its nuclear fuel, it can no longer support itself against the pull of gravity. This leads to a dramatic collapse of its core, followed by a tremendous explosion that ejects the star's outer layers into space. This explosion is what we call a supernova. The debris from a supernova is rich in elements like carbon, oxygen, and iron, which are produced during the star's life and amplified further in the explosion. When this material spreads throughout the galaxy, it enriches the interstellar medium, the gas and dust present between stars, with these essential building blocks. Over time, this enriched material can collect under the influence of gravity, forming clumps. As these clumps grow denser, they collapse even further, eventually reaching a stage where nuclear fusion ignites, marking the birth of a new star. This process illustrates a beautiful cycle in the cosmos. When one star dies in a spectacular explosion, it paves the way for new stars to form. Additionally, supernovas can trigger star formation in nearby regions by compressing clouds of gas and dust, nudging them closer together and sparking the conditions necessary for new stars to ignite. Thus, supernovas serve as both a destructive and a creative force, shaping the galaxy and contributing to the continuous cycle of stellar life and death. Observing the remnants of supernovas from Earth provides a fascinating glimpse into the life cycle of stars and the evolution of our universe. When a massive star reaches the end of its life, it undergoes a dramatic explosion known as a supernova. This explosion ejects material outward at incredible speeds, creating a colorful cloud of gas and dust. These remnants can be detected by astronomers using various techniques. One of the primary ways to observe supernova remnants is through telescopes that capture different types of light. These remnants emit visible light, which can be seen through optical telescopes. However, they also release energy in other forms, such as infrared, radio waves, and X-rays. By using specialized telescopes designed to detect these different wavelengths, scientists can gather a more complete picture of the remnants. For example, in the visible spectrum, the remnants often appear as bright, colorful structures. Certain gases, like hydrogen, can glow with distinctive colors. In the infrared range, cooler parts of the remnants emit heat, revealing compositions and structures that might be hidden from sight in visible light. Meanwhile, X-ray telescopes reveal high-energy processes and areas where the shock waves from the explosion collide with surrounding material. Additionally, ground-based and space-based telescopes are equipped with advanced technology that allows for the study of these remnants over time. By analyzing how these remnants change and evolve, scientists can learn about the dynamics of the explosion and the environmental conditions in the surrounding space. Furthermore, the distance of these remnants can be measured, enabling researchers to assess their sizes and the amount of material dispersed through space. This information not only enhances our understanding of supernova explosions, but also sheds light on the creation of elements that are essential for life, which are formed during such violent cosmic events. Through this combination of techniques and technologies, we can observe the remnants of supernovas, gaining insights into the life cycle of stars and the broader workings of our universe. A black hole is an incredibly dense region in space where the gravitational pull is so strong that nothing, not even light, can escape from it. To understand how this cosmic phenomenon forms, let's look at the life cycle of a star. Stars begin their lives as huge clouds of gas and dust, primarily hydrogen. Through a process called gravitational collapse, this material comes together, forming a dense core. As the core compresses, it heats up and eventually ignites nuclear fusion, allowing the star to shine brightly for millions or even billions of years. Over time, a star uses up the hydrogen fuel in its core and begins to fuse heavier elements. When a massive star approaches the end of its life, it undergoes dramatic changes. It can expand into a red giant, shedding its outer layers and leaving behind a hot, dense core. If this core is large enough, it won't just become a regular remnant like a white dwarf or neutron star. Instead, it will collapse under its own gravity. This core collapse continues until it reaches a point of infinite density, creating a singularity. Surrounding this singularity is an invisible boundary known as the event horizon. Once any matter or radiation crosses this boundary, there's no turning back. It's drawn into the black hole. The process is driven by the immense gravitational forces at play, which can warp space and time itself. So, a black hole isn't just a space disaster. It's an extraordinary result of stellar evolution, showcasing the dynamic life and death of stars in our universe. Black holes themselves do not emit light, which makes them invisible to the naked eye in traditional telescopes. However, scientists have found clever ways to observe their presence and influence on nearby matter. One of the most significant methods involves studying the behavior of stars and gas that are close to a black hole. When a star orbits a black hole, it can be seen moving in a rapid and unpredictable manner. By tracking these movements, scientists can infer the mass of the black hole exerting its gravitational pull. Another fascinating method comes from the material surrounding a black hole, often referred to as an accretion disk. This disk forms from gas and dust that spirals inwards. As this matter gets closer to the black hole, it accelerates and heats up to extremely high temperatures, emitting powerful radiation, especially in the form of X-rays. Observing this radiation allows scientists to detect the black hole indirectly. In recent years, advanced technology has enabled even more groundbreaking developments. The Event Horizon Telescope, a network of linked radio dishes around the world, was able to capture an image of the shadow of a black hole. This shadow is the outline of the black hole against the glowing gas of the accretion disk, providing direct evidence of its existence. Thus, by studying how objects behave in the vicinity of black holes and by detecting high-energy emissions from surrounding material, scientists have been able to gather substantial evidence of these mysterious cosmic phenomena, piecing together the puzzle of their existence despite their inherently invisible nature. The event horizon of a black hole is a boundary in space that holds great significance. Imagine it as an unseen line marking the point of no return. When anything crosses this threshold, it cannot escape, not even light. This is why black holes appear black. They trap everything that ventures too close. Understanding the event horizon helps us grasp the strange nature of black holes. It signifies where gravitational pull becomes so intense that space and time begin to behave unusually. Inside the event horizon, the rules of physics as we know them start to break down. Time can stretch and slow down, creating bizarre effects for observers at a distance. Scientists use the event horizon to study the mechanics of black holes, including how they grow and interact with their surroundings. Observing the light or energy emitted by material as it approaches this boundary gives valuable insights into the black hole's size, rotation, and the laws of physics under extreme conditions. The event horizon is a gateway into understanding some of the most puzzling elements of our universe, challenging our perceptions of reality and the fabric of space-time itself. Measuring the mass of a black hole might seem like a daunting task, but scientists have developed clever methods to do just that. Since black holes do not emit light, they cannot be measured directly. Instead, scientists look at the effects they have on their surroundings. One common approach involves observing the motion of stars or gas clouds near a black hole. Just like how you can judge how heavy a person is by the way they push against the ground when they move, the way objects move around a black hole can give clues about its mass. If a star is orbiting around an invisible object and moving quickly, it indicates that the object, in this case, the black hole, is very massive. Using the principles of gravity, scientists apply a fundamental rule. The strength of gravity from an object determines how fast other objects will move in its vicinity. By measuring the speed of the orbiting stars and the distance from the black hole, scientists can work out how much mass the black hole must have to exert that gravity. In addition, another technique involves examining the light emitted by hot gas as it spirals into a black hole. As this gas accelerates and heats up, it emits X-rays, high-energy light that can be detected by instruments. The behavior of this gas, how fast it moves, and how it interacts with the black hole can also provide valuable information about the black hole's mass. Finally, scientists can even study gravitational waves, ripples in space-time caused by massive objects colliding, such as two black holes merging. The way these waves spread out through space carries information about the masses of the black holes involved. By piecing together these observations and measurements, scientists can build a clearer picture and get a precise estimate of a black hole's mass, transforming mystery into knowledge about these extraordinary cosmic phenomena. Black holes are fascinating cosmic phenomena that come in several distinct types, each with its own unique characteristics. The most common classification divides them into three main categories: stellar black holes, supermassive black holes, and intermediate black holes. Stellar black holes form when massive stars exhaust their nuclear fuel and undergo a catastrophic collapse at the end of their life cycle. This collapse compresses the star's core, creating a region where gravity is so intense that not even light can escape. These black holes typically have masses greater than a few times that of our Sun, and they can often be detected by the light emitted when they pull in nearby gas and debris. Supermassive black holes are dramatically different. These giants can possess the mass equivalent to millions or even billions of suns. They reside at the centers of most galaxies, including our Milky Way. The origin of supermassive black holes is still a mystery, but they likely formed from the merging of smaller black holes and the accretion of vast amounts of gas and dust over billions of years. Their influence is so powerful that they help shape the structure of their host galaxies. Intermediate black holes represent a less common, though equally intriguing category. They have masses that fall between those of stellar and supermassive black holes. While their existence was once largely theoretical, recent observations suggest they may form from the merger of multiple stellar black holes in dense star clusters. These intermediate black holes could play a crucial role in understanding the evolution of galaxies. Additionally, there are theoretical black holes, such as primordial black holes, which could have formed shortly after the Big Bang. These black holes are thought to be very small and could vary widely in mass. However, their existence remains speculative, and more evidence is needed to confirm their presence. Each type of black hole provides insight into the mysteries of the universe, offering clues about star formation, galaxy evolution, and the fundamental laws of physics. As scientists continue to explore these cosmic giants, our understanding of the universe keeps expanding. A black hole profoundly influences both time and space in its vicinity. To understand this, imagine space as a stretched-out rubber sheet. When a heavy object, like a black hole, is placed on it, the sheet curves down significantly around that object. This curvature represents how gravity works. The greater the mass of an object, the more it distorts space around it. When it comes to time, the effects are just as dramatic. Think of time as a flowing river. Near a black hole, the river slows down considerably. If an observer were to watch someone close to a black hole, they would see that person's actions occur much more slowly compared to their own experience of time, which remains normal. This phenomenon is called time dilation, and it occurs because the intense gravity of the black hole warps both space and time, creating a curious relationship where they cannot be treated separately. As one nears the black hole, particularly at its boundary known as the event horizon, the effects become even more extreme. From the perspective of outsiders, someone falling into the black hole appears to move slower and eventually freeze at the edge, fading away slowly as light struggles to escape. However, for the person crossing into the black hole, they would not feel any difference initially. Instead, they plunge into a region where the rules of physics as we understand them begin to break down. The interplay of time and space around a black hole paints a fascinating picture of the universe's mysterious and extreme nature. The mystery of what lies beyond a black hole is one of the most intriguing questions in astrophysics. Traditionally, when we think about black holes, we imagine an impenetrable barrier beyond which nothing can escape, not even light. This leads to a region known as the event horizon, which acts as the point of no return. But what happens inside the black hole, or beyond its edge, remains a subject of great speculation and debate. One current theory is that beyond the event horizon, matter is crushed into an infinitely small point called a singularity. At this point, the laws of physics as we understand them cease to function normally. Time and space become incredibly warped, and our usual understanding of the universe does not apply. This suggests that the environment inside a black hole is vastly different from the one we experience. Another fascinating idea is the possibility of wormholes. Some scientists propose that black holes could connect to other regions of the universe, or even to other universes entirely, creating a bridge-like structure. This means that traveling through a black hole might not lead to oblivion, but could potentially open a doorway to an entirely different area of space and time. Additionally, there is a concept known as the information paradox, which challenges our understanding of what happens to information that falls into a black hole. According to quantum mechanics, information cannot be destroyed, yet if something disappears beyond the event horizon, it seems lost forever. Researchers are investigating whether the information might be preserved in some form at the event horizon, hinting that there may be a deeper layer of reality that we have yet to comprehend. Lastly, some theories suggest that black holes might be gates to parallel universes or alternate dimensions. This would fundamentally change our understanding of the cosmos, implying that the universe is much more interconnected than we currently perceive. Each of these theories opens up exciting possibilities and leads to new questions about the nature of reality, pushing the boundaries of science and our understanding of the universe we inhabit. Exoplanets are planets that exist outside our solar system, orbiting stars other than our Sun. Imagine the vast universe filled with countless stars, and each of those stars could potentially host its own planets. Exoplanets vary widely in size, composition, and distance from their host stars, giving scientists a rich field of study to explore. The discovery of exoplanets is an exciting and innovative process. While early observations relied on detecting changes in starlight, modern methods have become more sophisticated. One prominent technique involves monitoring stars for a slight dimming effect. When a planet crosses in front of a star from our perspective, it blocks a tiny amount of light, causing a brief decrease in brightness. This method is known as the transit method and has led to many confirmed discoveries. Another technique is radial velocity, which looks for the wobble of a star caused by the gravitational pull of orbiting planets. As a planet revolves around a star, its gravity pulls the star slightly, causing it to move in a small circle. This movement creates detectable changes in the star's light spectrum, revealing the presence of a planet. As technology advances, new methods continue to emerge, like direct imaging, where astronomers capture pictures of exoplanets by blocking out their star's light. Each of these methods expands our understanding of the universe, revealing a wealth of planetary systems, some potentially similar to our own. Exoplanets challenge our ideas about the formation of planetary systems and the possibilities for life beyond Earth. Determining the habitability of an exoplanet, which is a planet outside our solar system, involves a careful analysis of various factors. Scientists start by looking for planets located in what is known as the habitable zone around a star. This zone is the region where conditions might be just right for liquid water to exist, essentially the Goldilocks zone, where it's not too hot and not too cold. Essentially the Goldilocks zone, where it's not too hot and not too cold. Next, scientists analyze the planet's atmosphere. An atmosphere can protect a planet's surface from harmful radiation, help regulate temperature, and contain essential gases for life like oxygen and carbon dioxide. Instruments that measure light from the star as it passes through the planet's atmosphere can reveal its composition. If they find gases that suggest biological activity, that could be a promising sign. Temperature is also crucial. To determine if a planet could support life as we know it, scientists model its climate based on data gathered from its star. This includes understanding energy from the star, how much heat the planet retains, and how it compares to Earth. If temperatures are conducive to water remaining in liquid form, that's a positive indication. Another important aspect is the planet's geology. A planet with a solid surface and geological activity might have the potential for diverse environments which can support various forms of life. Scientists look for signs of geological processes like volcanism and plate tectonics that can create a dynamic ecosystem. Lastly, astronomers consider stellar conditions, like the type of star the planet orbits. Stars that burn steadily and have a long lifespan give planets more time to evolve and potentially support life. By combining all this information, scientists build a picture of an exoplanet's habitability. While no single factor is definitive on its own, together they help assess whether a distant world might host life. The search is ongoing, as new technologies and methods allow us to probe deeper into the mysteries of our universe. In the vast expanse of our galaxy, scientists have discovered numerous exoplanets, each unique and intriguing. One standout is a planet known for its extreme temperatures and weather. This world, often labeled a hot Jupiter, orbits very close to its star, making it sizzle with temperatures that could melt metal. Its atmosphere features winds howling at incredible speeds, creating dramatic storms that would be unimaginable here on Earth. Another fascinating find is a planet that has the potential to harbor water, an essential ingredient for life as we know it. Located in what scientists refer to as the habitable zone, this planet is at just the right distance from its star to allow for liquid water to exist. However, despite its potential for supporting life, we are still only beginning to understand its atmosphere and conditions. Then, there's a planet whose surface is mostly covered in lava, creating an otherworldly landscape filled with rivers of molten rock. Its perpetual volcanic activity paints a picture of intense geological processes that occur in real time, showcasing the dynamic nature of celestial bodies. One more intriguing exoplanet is actually a collection of planets circling a star known as a binary system. This system exists in varied and complex movement, demonstrating how planets can interact gravitationally, influencing one another in their dance through space. Observing these interactions helps scientists learn more about planet formation and movement. Finally, there's a planet that intrigues with its incredibly dense atmosphere made up predominantly of strange gases. Studies suggest it may even have clouds of gems raining down. Exploring this planet gives us insight into the rich diversity of planetary environments that exist beyond our own. These discoveries help expand our understanding of the universe, highlighting the many different environments that exist and pushing us to wonder what life could look like in those distant worlds. Each exoplanet contributes a new piece to the puzzle of our cosmic neighborhood, revealing the extraordinary possibilities that lie beyond Earth. Exoplanets are planets that exist outside our solar system, orbiting stars other than our Sun. They come in a remarkable variety, often differing greatly from the planets we know. While the planets in our solar system can be categorized into rocky planets and gas giants, exoplanets display a wider range of characteristics. Some exoplanets are enormous gas giants, much larger than Jupiter, while others might be small, rocky bodies resembling Earth or Mars. One striking difference is the types of orbits these exoplanets have. Many are found in very close proximity to their stars, resulting in extremely high temperatures, while others are in wildly elliptical orbits that bring them close and then far away from their stars. This variety creates circumstances that can lead to unique climate conditions, atmospheric compositions, and even possibilities for life that we cannot fully imagine yet. Additionally, some exoplanets have been identified as super-Earths, larger than Earth but smaller than the gas giants. These planets might possess thick atmospheres or even liquid oceans, leading to speculation about their habitability. The diversity of these alien worlds challenges our understanding of planetary formation and migration, revealing that the universe is likely filled with planets that do not fit neatly into our conventional categories. Exoplanets extend the boundaries of what we consider possible in planetary science, igniting curiosity about the vast array of worlds waiting to be discovered beyond our solar system. To uncover the secrets of the atmospheres surrounding distant worlds, astronomers employ several fascinating methods. One of the primary techniques is called spectroscopy. Imagine shining a light through a prism and watching it break into a rainbow. Similarly, when light passes through the atmosphere of a planet, it gets altered in unique ways, leaving behind a signature pattern, much like a fingerprint. By studying these patterns, scientists can determine the composition of the atmosphere, identifying gases like carbon dioxide, hydrogen, or even the presence of water vapor. Another method involves monitoring the transit of a planet as it crosses in front of its star from our viewpoint. During a transit, some of the star's light filters through the planet's atmosphere, absorbing certain wavelengths. By carefully analyzing this light before, during, and after the transit, astronomers gather information about the thickness and composition of the atmosphere, learning about its density and potential weather patterns. A technique called direct imaging also plays a crucial role. This approach focuses on capturing images of planets directly, separating their faint light from the overwhelming brightness of their stars. Using advanced instruments, astronomers can analyze the light reflected off these planets, revealing clues about their atmospheres and surface conditions. Lastly, some astronomers rely on data from space telescopes equipped with specialized sensors. These instruments can detect changes in the light of a star caused by the gravitational pull of an orbiting planet. This gravitational tug can hint at the planet's mass and size, contributing to our understanding of its atmospheric dynamics. Through these creative methods, astronomers continue to expand our knowledge of extraterrestrial atmospheres, piecing together the stories of worlds far beyond our own. The discovery of exoplanets, which are planets outside our own solar system, opens up fascinating possibilities for understanding life beyond Earth. Think of the universe as a vast ocean filled with countless islands. Each exoplanet represents one of those islands, some potentially capable of supporting life. By identifying and studying these distant worlds, scientists can explore different conditions that exist elsewhere, helping us to understand what environments might be suitable for life. One key aspect is the diversity of planetary systems. Some exoplanets are similar to Earth in size and temperature, situated within a zone where liquid water could exist. Water is essential for life as we know it, so finding these Earth-like planets encourages the search for signs of life. In contrast, other exoplanets can be gas giants or icy worlds, showcasing how varied conditions can be. This diversity allows scientists to consider a broader definition of what life could be, beyond just what we experience on Earth. Moreover, exoplanet studies give insight into the chemistry present on these distant worlds. By analyzing the light that filters through a planet's atmosphere when it passes in front of its star, scientists can detect specific gases. Some of these gases, when found together, may indicate biological processes similar to those on our planet. Detecting gases like oxygen or methane, for example, could suggest that some form of life is present. Finally, the search for exoplanets raises philosophical questions about our place in the universe. The more we find planets that could sustain life, the the more likely it is that we are not alone. This possibility inspires new research and explorations, pushing the boundaries of our knowledge and technology while igniting curiosity among people everywhere. Essentially, every new exoplanet discovered invites us to rethink what life might be, where it exists, and how we fit into the grand tapestry of the cosmos. Scientists have increasingly turned their gaze toward exoplanets, those planets that orbit stars outside our solar system, in the search for intelligent life. The sheer number of stars in our galaxy suggests that many of them likely host planets, and some of those planets may reside in a habitable zone where conditions could support liquid water and potentially life. Researchers believe that certain factors increase the chances of finding intelligent beings. These include the planet's size, which should ideally be similar to Earth's, allowing for a stable environment. A suitable atmosphere is crucial, providing the necessary elements for life and protection from harmful cosmic radiation. Additionally, a planet located at the right distance from its star can maintain temperatures conducive to life. Astrobiologists also consider the age of a planet. Life on Earth took billions of years to evolve into complex organisms, so a planet that is too young might not yet host intelligent life. Conversely, an ancient planet could have already advanced civilizations, or it may have gone through environmental changes that made it uninhabitable. While finding signs of microbial life is more feasible, signals or signatures of intelligent civilizations present a more complex challenge. Scientists are developing new technology to detect unusual atmospheric compositions that could indicate industrial activities or communication. The search for these biosignatures and technosignatures, evidence of technological processes, drives much of the current research. The Fermi paradox illustrates a key point. If intelligent life is common in the universe, why hasn't it been detected yet? Various hypotheses attempt to answer this, including the idea that intelligent civilizations may be incredibly rare. Technologically advanced societies might self-destruct, or they could simply choose not to communicate with us. Thus far, we have not made definitive contact with extraterrestrial intelligent life, but the possibilities lead to an exciting frontier of research. Future telescopes and space missions aim to take us closer to unraveling the mysteries of the cosmos, potentially revolutionizing our understanding of life beyond Earth. Dark matter is an invisible substance that makes up a significant part of our universe, yet it cannot be seen directly. Picture walking in a dark room. You can't see the furniture, but you know it's there because you bump into it. Similarly, scientists observe the effects of dark matter through its gravitational influence on visible matter, such as galaxies and galaxy clusters. In our universe, galaxies spin at such speeds that they should break apart if only the visible matter was present. However, they stay intact because dark matter surrounds them, acting like a glue that holds everything together. It's like an unseen hand exerting a pull that keeps the structure of galaxies stable. Understanding dark matter is crucial for several reasons. First, it helps explain the behavior and formation of galaxies. Without dark matter, our models of the universe would not work, and we would struggle to understand why galaxies look the way they do. Second, dark matter plays a vital role in the evolution of the universe. It is thought to influence the distribution of galaxies throughout cosmic history. As the universe expands, dark matter's presence shapes how galaxies cluster and interact with one another. Moreover, the study of dark matter raises fundamental questions about the very nature of reality. What is it made of? Why is it so abundant? Each clue to the mystery of dark matter brings us closer to understanding the broader structure of the cosmos. Unraveling the secrets of dark matter could transform our grasp of the universe and the forces that govern it, making it a cornerstone of modern astrophysics. Dark matter remains one of the universe's greatest mysteries, primarily because it cannot be seen directly. However, astronomers have inferred its existence through several compelling observations and calculations. One of the key pieces of evidence comes from the way galaxies rotate. When scientists observe these vast collections of stars, they notice something unusual. The outer parts of galaxies spin at speeds that seem to go against what would be expected based on the visible matter alone. In a typical scenario, the outer regions of a galaxy should rotate more slowly than the center, where most of the material is found. Instead, the stars and gas far from the core move at similar speeds to those closer in. This suggests that there is much more mass in each galaxy than what we can see, mass that doesn't emit light or energy and is hence invisible. Another significant clue comes from galaxy clusters. When astronomers observe these clusters, they find that the gravity holding them together is much stronger than what would be expected from the luminous matter alone, like galaxies and gas that can be seen with telescopes. The dynamics of these clusters imply that an unseen form of matter contributes a substantial amount of mass, generating extra gravitational pull. Further evidence arises from the behavior of light, specifically through a phenomenon called gravitational lensing. This occurs when light from a more distant object, like a galaxy, is bent around a massive object, such as a galaxy cluster, located between the observer and the distant object. The amount of bending is proportional to the mass of the foreground object. Scientists have observed that the extent of this bending indicates much more mass is present than can be seen. Together, these observations create a strong case for the existence of dark matter. It suggests there is a mysterious, invisible substance that interacts with regular matter through gravity, influencing the structure and behavior of the universe on the largest scales. The ongoing search for dark matter is crucial because understanding it could unlock secrets about the cosmos and its formation. The search for dark matter is an exciting journey that scientists are actively undertaking, as this mysterious substance makes up a significant portion of the universe's mass, yet does not interact with light, making it invisible and elusive. Various experimental methods are employed to try to uncover its secrets. One of the prominent techniques involves using large underground laboratories. These facilities are situated deep below the Earth's surface to shield sensitive equipment from cosmic rays and other forms of radiation that could interfere with measurements. Here, scientists utilize detectors filled with special materials that might interact with dark matter particles. When a dark matter particle collides with an atom in the detector, it can produce small flashes of light or generate slight movements in the atoms. By measuring these tiny signals, researchers hope to identify the presence of dark matter. Another approach relies on particle colliders, such as the Large Hadron Collider. In these high-energy environments, particles are smashed together at incredible speeds, potentially creating new particles. Some of these particles could be evidence of dark matter. Scientists carefully analyze the aftermath of these collisions, looking for unexpected results that could indicate the existence of dark matter particles or other related phenomena. Observational methods also play a crucial role. Astronomers study galaxies and cosmic structures to see how they behave under the influence of gravity. Dark matter doesn't emit light, but its presence is inferred from the gravitational effects it has on visible matter. For instance, when scientists observe how galaxies rotate, they find that the outer regions move much faster than expected, based solely on the visible matter. This discrepancy suggests that much more mass exists in the form of dark matter, providing a clue to its nature. Additionally, experiments are being conducted to investigate signals from dark matter interactions, such as those predicted by certain theoretical models. These experiments often use extremely sensitive detectors designed to spot rare and subtle interactions that might suggest dark matter's presence. Through these various methods, scientists are piecing together the puzzle of dark matter, hoping to unveil the properties of this enigmatic component of the universe and ultimately understand its crucial role in the cosmos. Dark energy is one of the greatest mysteries in modern astrophysics, playing a crucial role in the expansion of the universe. To understand dark energy, think of the universe as a balloon that is steadily expanding. When it comes to the universe, scientists observe that not only is it expanding, but the rate of this expansion is actually increasing over time. This puzzling observation led to the discovery of dark energy. Imagine that as the balloon inflates, there is an invisible force pushing it outward, making it grow faster. Dark energy serves as that force. Although it comprises a significant portion of the universe, accounting for nearly 70% of its total energy content, it remains elusive. It cannot be directly observed. Instead, scientists infer its existence by studying the motion of galaxies and the cosmic microwave background, the faint glow left from the Big Bang. The exact nature of dark energy is still unknown. Some theories suggest that it may be a property of space itself, meaning that as space expands, more dark energy is created. Others propose that it could be a dynamic field that changes over time. Regardless of its nature, dark energy has profound implications for the fate of the universe. If it continues to dominate, the universe will keep expanding at an accelerated rate, leading to a future where galaxies drift further apart and stars ultimately fade away. This idea paints a picture of a cold, dark universe over immense stretches of time, a stark contrast to the dynamic cosmos we see today. Dark matter and dark energy are two of the greatest mysteries in modern physics, significantly challenging our understanding of the universe. To grasp their impact, let's first understand what they are. Dark matter is an unseen substance that does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. It makes up a significant portion of the universe's total mass, yet we know very little about its true nature. Its presence explains why galaxies rotate at such high speeds without flying apart. There's additional mass exerting a gravitational pull that we cannot see. On the other hand, dark energy is thought to be responsible for the accelerated expansion of the universe. Imagine blowing up a balloon. As you blow air into it, the surface stretches and expands. Similarly, the universe is stretching, and dark energy serves as a mysterious force driving this acceleration. Dark energy constitutes a large part of the universe, but remains elusive in our understanding. Together, these phenomena reveal serious gaps in our existing models of physics. Traditional theories of gravity, primarily based on the work of Isaac Newton and Albert Einstein, struggle to account for the effects we observe. These models predict certain behaviors based on visible matter, yet dark matter and dark energy imply that there is a lot we cannot see or fully comprehend, leading to questions about the very fabric of space and time. Current models attempt to incorporate dark matter and dark energy, but they create complications in understanding fundamental forces and the overall composition of the universe. Theories like the Standard Model of particle physics do not include dark matter and offer no explanation for dark energy. Researchers are beginning to explore beyond these established theories, looking towards innovative concepts that could better describe our universe. As scientists seek answers, experiments and observations continue, pushing the boundaries of our knowledge. The revelations surrounding dark matter and dark energy challenge not only our scientific models, but also our philosophical understanding of reality, highlighting how much of the universe remains a profound mystery waiting to be explored. Dark energy remains one of the greatest mysteries in modern physics, and scientists have proposed several leading theories to explain its puzzling nature. At its core, dark energy is thought to be responsible for the accelerated expansion of the universe, which means that galaxies are moving away from each other faster over time. One prominent theory is the cosmological constant, initially introduced by Albert Einstein. This idea suggests that dark energy is a constant energy density that fills space uniformly. Imagine a tension in the fabric of space itself, pushing galaxies apart consistently throughout the vast universe. This model is quite simple and aligns well with many observations, making it a strong contender to explain the phenomenon. Another hypothesis is related to dynamic fields known as quintessence. Unlike the cosmological constant, which remains constant, quintessence postulates that dark energy can change over time. By thinking of quintessence as a type of fluid that evolves, scientists imagine a scenario in which its energy density fluctuates, affecting the rate of expansion in varying ways across cosmic history. Additionally, some researchers explore modifications of gravity as an explanation for dark energy. These models suggest that our current understanding of gravity, based on Einstein's theory, may need adjustment at vast scales. By modifying how gravity behaves in wide regions of space and time, they aim to account for the universe's accelerated expansion without relying solely on dark energy. There are even more unconventional ideas, such as the existence of extra dimensions of space. In these scenarios, the universe we're familiar with could be just a slice of a larger reality. If additional dimensions interact in specific ways, they might create effects similar to dark energy, influencing the expansion of our universe. As scientists continue to gather data from telescopes and experiments, they hope to refine these theories, leading us closer to understanding the true nature of dark energy and its role in the cosmos. The quest to unlock this cosmic riddle is still underway, with each discovery shedding light on the vast mysteries that lie beyond our sight. Dark matter and dark energy are two of the most mysterious components of our universe, and they hold critical clues about its fate. Imagine the universe like a gigantic balloon that is not just inflating, but also being pulled in different directions by invisible forces. Dark matter acts like the glue holding galaxies and galaxy clusters together, forming a sort of scaffolding that shapes the structure of the universe. Although we cannot see it directly, its influence is clear through the way galaxies rotate and move. The existence of dark matter helps explain how galaxies can spin at speeds that would send them flying apart if only the visible matter, like stars and planets, were present. On the other hand, dark energy is responsible for the accelerating expansion of the universe. Think of it as a mysterious force that pushes the universe apart, causing galaxies to move away from each other at increasing speeds. This expansion began after the Big Bang, and the role of dark energy seems to be growing stronger as the universe ages. This is why scientists describe dark energy as a repulsive force, one that dominates the universe's expansion over time. Understanding dark matter and dark energy is crucial because they help us predict how the universe will evolve. Scientists are trying to unravel the nature of these phenomena to answer fundamental questions about the universe's destiny. For instance, will the universe continue to expand indefinitely, growing colder and emptier? Or could gravitational attractions from dark matter lead to a reversal, causing everything to collapse back into a singularity? Each piece of information we glean about dark matter and dark energy brings us closer to these profound answers, revealing secrets that could fundamentally change our understanding of existence itself. Galaxies are vast collections of stars, gas, dust, and dark matter. Their formation begins in the early universe, where tiny fluctuations in density caused clouds of gas and dust to clump together. Over time, influenced by gravity, these clumps draw in more material, growing larger and denser. Imagine pouring honey onto a plate. It gathers in blobs that eventually connect, creating larger pools. This is similar to how galaxies start to form. As the gas and dust come together, they can become hot and collapse into stars. These early stars often form in clusters. As they burn brightly for millions of years, they create heavier elements through nuclear fusion. When these stars reach the end of their lives, they explode in supernova, scattering these elements back into space. This process enriches the surrounding gas, paving the way for the next generation of stars to form. Over billions of years, galaxies evolve in various ways. They can merge with other galaxies, creating larger structures. Picture two rivers joining into a larger one. This merger can lead to new star formation as the gases mix and compress. The interconnectedness of galaxies creates a complex web in the universe, and they can influence one another's formation through their gravitational pulls. Galaxies also change in shape over time. Some become spiral galaxies, characterized by their spinning arms that have new and bright stars, while others evolve into elliptical galaxies, which are more rounded and often contain older, dim stars. The ongoing exchange of gas and stars between galaxies helps drive this evolution. As we observe galaxies today, we see many in different stages of development, from young, actively forming galaxies to older ones with mature stars. Understanding their formation and evolution helps us grasp the history of the universe itself, showing how structures have changed and adapted over time, shaped by the dynamic forces of gravity, pressure, and star formation. The universe is home to a marvelous variety of galaxies, each offering a unique glimpse into the cosmos. The first major type is the spiral galaxy, which resembles a swirling pinwheel. These galaxies have central bulges surrounded by flat disks of stars, gas, and dust, often with long, beautiful arms extending outward. Our own Milky Way is an example of a spiral galaxy. Then we have elliptical galaxies, which are more rounded or elongated in shape. These galaxies typically contain a smooth, featureless profile, consisting mostly of older stars, with very little new star formation taking place. They can range from nearly spherical to more elongated shapes. Next, there are irregular galaxies, which do not fit neatly into the other categories. These galaxies are often chaotic in appearance, lacking a distinct form. They may contain regions of active star formation and exhibit a variety of structures. These galaxies often arise from gravitational interactions, like galactic collisions, which disrupt their shape. Finally, we encounter lenticular galaxies. These represent a middle ground between spiral and elliptical types. They have a central bulge similar to elliptical galaxies and a disk like spiral galaxies, but they lack significant spiral arms. This gives them a flattened shape that still retains some features of both. Each of these galaxy types varies not only in shape, but also in the stars they contain and the processes happening within them. This research not only enhances our understanding of the evolution of stars and galaxies, but also allows us to explore fundamental questions about the nature of gravity itself and its role in the fabric of the universe. Each detection brings new information, helping scientists to map out events that have shaped the cosmos, all while expanding our knowledge of how space-time behaves under extreme conditions. The curvature of space-time is a fundamental concept in understanding how massive objects interact with the universe around them. Imagine space-time as a vast, flexible sheet stretched across the cosmos. When a heavy object, like a planet or a star, sits on this sheet, it creates a dip or curve. The greater the object's mass, the deeper and wider the curve. This bending of the sheet represents how the massive body influences the fabric of space-time itself. When other objects, such as smaller planets, asteroids, or even light, come near this curve, they are drawn toward the mass. It's similar to rolling a marble towards the curved surface created by a bowling ball. The marble follows the path dictated by the curve, which appears as if the bowling ball is pulling it in. This is how gravity works, according to Einstein's theory of general relativity. Furthermore, this curvature doesn't just affect objects with mass, it also modifies how time flows. Near a massive body, time actually passes more slowly compared to areas far away from that mass. This intriguing phenomenon reflects the interconnectedness of space and time. They are not separate entities, but rather part of a dynamic system that responds to mass. Thus, the curvature of space-time reveals the profound impact of gravity, showing that massive objects don't just exert force in a conventional sense. Instead, they shape the very geometry of space-time itself, altering the paths of objects and the flow of time in their vicinity. Through this understanding, we can grasp why the universe behaves the way it does, from the orbits of planets to the bending of light around distant stars. Astronomers have a fascinating tool at their disposal called time dilation, which allows them to study distant cosmic phenomena in a unique way. Time dilation occurs due to the effects of gravity and speed on the flow of time, as proposed by Einstein's theory of relativity. In simpler terms, time is not the same everywhere in the universe. It can stretch or compress depending on how fast you are moving or how strong the gravitational field is. When astronomers observe objects that are incredibly far away, like distant stars or galaxies, they are looking back in time. This is because light from those objects takes a long time to reach us. If a star is millions of light years away, for example, we are seeing it as it was millions of years ago. However, the influence of time dilation means that the light from very fast-moving objects, like jets from black holes or exploding stars, can tell us even more. For instance, when a supernova explodes, the events can unfold rapidly. If the explosion is moving away from us at a significant fraction of the speed of light, the light waves become stretched out. This means those events appear to take longer than they actually do. By carefully measuring the differences in how long events take to occur, scientists can infer the speeds at which these cosmic events are happening and the effects of gravity on them. Moreover, time dilation can help astronomers determine distances in the universe. By observing how time is affected in different gravitational fields, astronomers can map out the structure of galaxies and clusters. They can even gauge distances by estimating how light from distant objects is altered as it interacts with gravity along its path. In this way, time dilation is not just a curious phenomenon, it's a vital concept that supports our understanding of the universe. It allows astronomers to piece together the dynamic nature of cosmic events, enriching our knowledge of the vast and complex cosmos we inhabit. As we look toward the future, our understanding of space and time is certainly poised to evolve, reflecting advancements in technology and discovery. Historically, the way we perceive these concepts has already shifted dramatically. For centuries, space was viewed as a vast emptiness, while time was seen as an absolute constant. But with breakthroughs in physics and astronomy, we've begun to grasp that space and time are interconnected, forming what we call space-time. In the coming decades, we may gain deeper insights into this relationship. For instance, ongoing research into phenomena like black holes or gravitational waves could reveal new aspects of how gravity affects not only the fabric of space, but also the passage of time itself. Imagine realizing that time might not always flow at a constant rate everywhere. Depending on factors like gravity or speed, it could stretch or compress, altering our very understanding of cause and effect. Quantum mechanics, which explores the behavior of tiny particles, could also reshape our views. If scientists continue to uncover the principles that govern these particles, it may suggest that space and time are not so solid, but could instead be more like fluid concepts capable of bending and changing under certain conditions. Moreover, advancements in technology, such as powerful telescopes and computer simulations, will help us observe parts of the universe we've never seen before. This could lead to discoveries about the nature of black holes, dark matter, and dark energy, mysteries that currently challenge our comprehension of space and time. As we venture into deeper space through robotic missions and potential human travel to Mars or beyond, the experiences of crew members could also provide new perspectives on how life in different gravitational environments influences time perception and physical processes. The next few decades hold the potential for significant breakthroughs in our understanding of space and time. By exploring the frontiers of science, we may unravel deeper truths about the universe, changing the way we think about existence itself. Nebulae are incredible regions of space filled with gas and dust, acting as the birthplaces of stars and planets. Their formation begins when massive stars exhaust their nuclear fuel and explode in luminous events known as supernovae. This explosion scatters the star's material into space, creating an enriched cloud of gas and dust. In addition to supernova remnants, nebulae can also form from the slow shedding of material from aging stars, particularly those that have become red giants. These stars lose their outer layers, which then cool and drift in space, forming what we call a planetary nebula. Another important source of nebulae is the accumulation of gas and dust from the interstellar medium, which serves as the raw ingredients for new stars. Nebulae play a crucial role in the life cycle of the universe. They are the incubators where stars are born, and as new stars form, they illuminate the surrounding gas and dust, often creating beautiful displays of color. The process of star formation within nebulae leads to the creation of planetary systems, including those like our own. Thus, the gas and dust in nebulae not only contribute to the formation of stars, but also carry the essential elements needed for life, making them key components in the cosmic ecosystem. Without nebulae, the universe would lack the diversity of stellar and planetary bodies that we observe today. Quasars are among the brightest and most powerful objects in the universe, and they emit an enormous amount of energy. At their core, quasars have supermassive black holes surrounded by a swirling disk of gas and dust. This disk, often referred to as an accretion disk, is incredibly hot due to the intense gravitational forces at play. As matter spirals inward towards the black hole, it speeds up and heats up, reaching temperatures so extreme that it emits tremendous amounts of light and other forms of radiation, including X-rays. This energy output can be so great that a single quasar can outshine entire galaxies. Observing quasars allows astronomers to gain insight into the early universe. Many quasars are found at vast distances from Earth, meaning we are seeing them as they were billions of years ago, shortly after the Big Bang. By studying their light, scientists can learn about the conditions in the universe when it was young and how galaxies formed and evolved over time. Quasars serve as cosmic beacons, illuminating the regions around them and allowing researchers to investigate the intergalactic medium, the space between galaxies. The way light from a quasar interacts with the gas and dust it travels through provides clues to the composition and density of the early universe. Through these observations, quasars play a crucial role in deepening our understanding of cosmic history and the evolution of the universe. Pulsars are fascinating celestial objects that represent a specific type of neutron star. After a massive star exhausts its nuclear fuel, it undergoes a supernova explosion, leaving behind a dense remnant. When this remnant is smaller than a certain size, it collapses into a neutron star, which is incredibly dense. A mass greater than that of our Sun, squeezed into a space only about as wide as a city. What makes pulsars particularly interesting is their rapid rotation and the beams of radiation they emit. Think of a pulsar as a cosmic lighthouse. As this neutron star spins, it emits beams of electromagnetic radiation from its magnetic poles. If these beams point toward Earth, we detect them as regular pulses of radiation. This is much like how a lighthouse beam is only visible when it faces you. The rotation speed of some pulsars is so rapid that they can spin multiple times per second, creating a rhythmic pulse that can be detected with sensitive instruments. To detect pulsars, scientists use radio telescopes, which are large antennas designed to pick up radio waves from space. When a pulsar emits its radiation, the radio telescope picks up these signals, which appear as periodic pulses in the data. By studying the timing of these pulses, astronomers can determine the pulsar's rotation speed, magnetic field strength, and even the environment around it. The discovery of pulsars was a monumental achievement in astrophysics, as it offered new insights into the nature of neutron stars and the fundamental forces shaping our universe. Cosmic rays are like messengers from space, traveling through the universe and bringing crucial information about the cosmos. These high-energy particles, primarily protons and atomic nuclei, originate from various sources, including exploding stars, active galaxies, and possibly even our own Sun. As they rush through space at nearly the speed of light, cosmic rays interact with the matter they encounter, impacting everything from planetary atmospheres to human technology. One of their significant roles is in the formation of new elements. When cosmic rays collide with atoms in the atmosphere, they can produce secondary particles and trigger nuclear reactions that lead to the creation of elements like carbon and nitrogen. This process contributes to the chemical diversity necessary for life as we know it, fostering the very building blocks that form the foundations of organic matter. Cosmic rays also play a role in understanding our universe's magnetic fields. As these particles pass through different regions of space, they can reveal how magnetic fields shape cosmic structures. By studying their paths and interactions, scientists gain insights into the invisible forces that guide stars, galaxies, and even the large-scale structure of the universe itself. Moreover, cosmic rays can affect the Earth's climate. They influence cloud formation by interacting with our atmosphere, potentially contributing to weather patterns. When they collide with air molecules, they create ions that encourage condensation and help form clouds. This connection has sparked research into how variations in cosmic ray intensity might impact long-term climate changes on our planet. Cosmic rays serve as key players in the universe, influencing elemental creation, enhancing our understanding of cosmic phenomena, and playing a potential role in our climate systems. Their study reveals not only the dynamic nature of the universe, but also our place within it. Gamma-ray bursts are among the most powerful explosions in the universe, and identifying them involves a combination of advanced technology and a keen understanding of cosmic events. Instruments designed to detect high-energy radiation are deployed in space, constantly monitoring for bursts of gamma rays. These instruments can pick up sudden increases in gamma-ray emissions that last from milliseconds to several minutes. When a burst occurs, it sends out a flood of energy across vast distances, which can be detected as a short-lived flash of light in the gamma-ray spectrum. The underlying causes of gamma-ray bursts are typically associated with two major cosmic events. One leading scenario is the collapse of massive stars. When a star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse, resulting in an explosion called a supernova. If the initial core is sufficiently massive, it may create a black hole, and the matter falling into that black hole can produce intense jets of energy, resulting in a gamma-ray burst. Another scenario involves the collision of neutron stars, which are incredibly dense remnants of exploded stars. When two of these neutron stars spiral toward each other and eventually collide, it leads to the release of a tremendous amount of energy. This event can also produce gamma-ray bursts. In both cases, the high-energy emissions are a sign of catastrophic transformations in the universe that can be detected light years away. By studying these bursts through their gamma-ray emissions and analyzing the light that follows them, astronomers can learn more about the origins and impacts of these extraordinary cosmic occurrences. Magnetars are a special type of neutron star known for their extraordinary magnetic fields. To understand what sets them apart, let's start with neutron stars themselves. When a massive star runs out of fuel, it can explode in a supernova. What remains is an incredibly dense core that collapses into a neutron star, which is typically about the mass of the Sun but squeezed into a space no larger than a city. Now, most neutron stars have strong magnetic fields, but magnetars take this to an extreme. Their magnetic fields can be 1,000 trillion times stronger than that of Earth. This intense magnetism profoundly influences their behavior, resulting in unique phenomena such as bursts of X-rays and gamma rays, which are much more energetic than what is typically seen from other types of stars. These powerful bursts are not just random, they occur due to the decay of the magnetar's magnetic field, releasing energy that can be detected across vast distances in space. Unlike regular neutron stars, which may be relatively stable, magnetars can have sudden outbursts and display highly variable emissions that change dramatically over short periods. What makes magnetars truly captivating is their extreme magnetic fields, which lead to extraordinary emissions and dynamic behaviors that make them stand out among the myriad of celestial bodies in our universe. They give us a glimpse into the limits of physics and the fascinating role that magnetism plays in shaping celestial phenomena. When two black holes merge, they create one of the most energetic events in the universe. This phenomenon is like witnessing a cosmic dance, where these massive objects spiral towards each other and ultimately combine, releasing energy in the form of gravitational waves. These waves ripple through space-time, traveling vast distances before reaching us. By capturing these waves, scientists have opened a new window into the universe, allowing them to study events that were previously invisible. Understanding black hole mergers helps physicists test and refine theories of gravity, especially Einstein's theory of general relativity. When two black holes collide, they behave according to the predictions of this theory. By observing the details of the wave patterns produced during the mergers, scientists can confirm whether these predictions hold true or if adjustments are needed. Each observation is like a puzzle piece that enhances our understanding of how gravity operates under extreme conditions. Moreover, these mergers provide insight into the formation and evolution of black holes themselves. By studying the characteristics of the resulting black holes, researchers can learn about the life cycles of these enigmatic entities and how they interact with their surroundings. This knowledge expands our comprehension of the dynamics of the universe and the role black holes play in it. Black hole mergers also have implications for the broader field of astrophysics, shed light on the density and distribution of dark matter, and even inform our understanding of the early universe. As we gather more data from these spectacular events, we build a more complete picture of our cosmos, one that transforms our fundamental understanding of nature and the universe itself. Every merger is a profound invitation to explore the mysteries of physics that govern existence. Living in space presents unique challenges for astronauts, as the environment is drastically different from Earth. One of the most significant changes is the lack of gravity. In space, everything floats, which affects how astronauts move, eat, and even sleep. To adapt to this weightlessness, astronauts undergo extensive training both before and during their missions. They practice moving in a zero-gravity environment, learning to control their movements to prevent themselves from floating uncontrollably. To deal with daily tasks, astronauts use specially designed tools and appliances. For example, meals are pre-packaged and often require heating. Eating in zero gravity means food adheres to surfaces rather than falling, so they use utensils that prevent spillage. Drinking is also different. Astronauts use pouches with straws to sip their beverages because they can't rely on gravity to help. Their bodies also undergo changes in space. Without the constant pull of gravity, muscles and bones can weaken over time. To counteract this, astronauts follow rigorous exercise routines each day using resistance machines and stationary bicycles to maintain their strength and bone density. In addition, they must ensure they stay hydrated and balanced in nutrients, closely monitoring their diets. Psychologically, the isolation and confinement in a spacecraft can be challenging. Astronauts are selected not only for their scientific skills, but also for their mental resilience. They undergo psychological evaluations and training to help them cope with the stresses of being away from home for extended periods. Regular communication with family and support teams on Earth plays a vital role in maintaining their well-being. Overall, adaptation to living in space is a multifaceted process, requiring astronauts to adjust physically, mentally, and emotionally to thrive in an environment that is inherently different from our home planet. Space explorers face a unique set of psychological challenges that stem from the isolation, confinement, and distance of their environment. Imagine being in a metal tube, far removed from the comforts of Earth, surrounded by the vast emptiness of space, and relying on a small team for support. The feeling of isolation can weigh heavily on an astronaut's mind. With no familiar sights, sounds, or landscapes, loneliness can creep in, leading to feelings of sadness or even despair over time. Moreover, living in cramped quarters can cause tension among crew members. Close proximity to others, combined with the high-stakes nature of their work, can exacerbate conflicts. It's like being at a small gathering where everyone must get along perfectly. Any small disagreement can quickly escalate into a significant issue. To mitigate such tensions, astronauts undergo extensive training in communication and teamwork, preparing them to work as a cohesive unit. Another challenge is the disruption of natural rhythms. Space missions can alter sleep patterns with the absence of day and night cycles. This change can lead to fatigue and impact overall mental well-being, making even basic tasks feel overwhelming. Maintaining a healthy routine is crucial, and astronauts must develop strategies to ensure they rest adequately and manage their time effectively. Furthermore, the uncertainty of space travel adds layers of stress. Every mission carries inherent risks, from technical malfunctions to the possibility of a health emergency. Knowing that help is thousands of kilometers away can lead to anxiety. Astronauts train to stay calm under pressure, but the constant awareness of potential danger can still take a toll on mental health. Lastly, there is the challenge of readjusting to life on Earth after a mission. Returning from space can feel quite disorienting. Observational differences, such as gravity and the bustling environment of home, can be overwhelming. This transition requires support and adaptation strategies as astronauts reacquaint themselves with everyday life after experiencing the extraordinary. Overall, while space exploration is a remarkable endeavor, it comes with significant psychological hurdles. Addressing these challenges is essential for ensuring that explorers can safely carry out their missions and return home healthy in mind and body. Microgravity, the condition experienced in space where gravity is much weaker than on Earth, has profound effects on the human body during extended missions. When astronauts are in this environment, their bodies undergo significant changes due to the lack of gravitational force. One of the most noticeable effects is muscle atrophy, where muscles weaken and shrink because they don't have to support the body's weight as they do on Earth. This reduction in muscle mass can lead to decreased strength and endurance. Bone density also suffers in microgravity. In a gravitational environment, our bones constantly resist the pull of gravity, which helps maintain their strength. However, in space, this resistance diminishes, leading to a loss of bone mass. Over time, astronauts can experience conditions similar to osteoporosis, making their bones more fragile and susceptible to fractures. Another notable change occurs in the cardiovascular system. The heart and blood vessels adapt to the reduced need for blood circulation. In space, the heart can become more spherical instead of the typical shape developed on Earth, and astronauts may experience a decrease in cardiovascular fitness. This can make the body less efficient at pumping blood, which poses risks upon returning to Earth's gravity. Moreover, fluid distribution in the body shifts. In microgravity, bodily fluids like blood and water tend to move upwards, causing a puffy appearance in the face. This alteration can also affect vision, leading some astronauts to experience problems with their eyesight. Psychologically, the isolation and confinement of space missions can impact mental health. The crew members may feel stressed or anxious due to the limited social interactions and the challenges of living in a closed environment. Understanding these changes is essential for preparing astronauts for long-duration missions, such as those to Mars. Engineers and medical scientists continuously seek ways to mitigate these effects, ensuring that astronauts can maintain their health and performance throughout their missions in the challenging environment of space. To sustain human life on another planet, a series of technological advancements are essential. First and foremost, we need life support systems that can provide essential requirements such as breathable air, clean water, and nourishing food. This involves developing effective recycling systems that can continuously filter and reuse resources. Imagine an environment where every breath you take and drop of water you use can be captured, purified, and reused over and over again. Next is the technology to produce food in space. This could mean growing plants in controlled environments, utilizing hydroponics or aeroponics. These methods allow for agriculture without soil, using nutrient-rich water or mist to nourish the plants. Such systems not only supply food, but also contribute to oxygen production and carbon dioxide absorption. In addition, habitats will need to be built to protect human inhabitants from harsh planetary environments. These structures must shield occupants from radiation, extreme temperatures, and dust storms. Advanced materials and designs, inspired by our understanding of physics and engineering, can help create livable spaces that are both strong and energy efficient. Energy is another crucial aspect. Power generation systems such as solar panels need to be adapted for use on distant planets where sunlight may differ from Earth. Other possibilities include nuclear energy as a reliable source, or even harnessing energy from the planet's own resources, like geothermal. Transportation technology is also vital for moving people and supplies on the planet itself and for travel to and from Earth. This includes rovers and advanced vehicles designed to navigate varying terrains, as well as systems to transport cargo safely. Finally, communication systems that can operate over vast distances are essential. This technology would allow astronauts to stay in contact with mission control on Earth, share data, and receive timely support. The integration of all these technologies will not only facilitate survival, but also make exploration and long-term habitation a reality on other worlds. The idea of human settlement on Mars has sparked excitement and ambition among scientists and space enthusiasts. Currently, various space agencies and private organizations are developing plans to establish a human presence on the Red Planet. The vision is to create a sustainable habitat that allows humans to live, work, and thrive in the harsh Martian environment. One option includes sending missions with advanced teams of robots that would prepare the area for human arrival. These robots could build habitats, extract water from the soil, and generate energy from the sun. The goal is to create an infrastructure that supports human life before people actually set foot on Mars. This helps minimize risks and ensures that food, water, and energy sources are readily available when astronauts arrive. However, settling on Mars poses significant challenges. The planet's atmosphere is incredibly thin, composed mostly of carbon dioxide, which means humans can't breathe without assistance. Protective habitats will be necessary to shield settlers from both this hostile air and the intense radiation from space. Durable materials and advanced technologies will need to be developed to create such shelters. Another major concern is transportation. Getting humans to Mars requires powerful rockets and reliable spacecraft that can withstand long journeys through space. The duration of travel to Mars could take several months, and that length of time demands systems capable of supporting life for extended periods without resupply from Earth. Health is also a critical focus. Mars has lower gravity than Earth, which affects how the human body reacts over time. Astronauts could face challenges with muscle loss and bone density. Research is ongoing to understand these effects better and find ways to mitigate them, like fitness regimens and nutritional plans tailored for this new environment. Finally, the psychological aspects of living on another planet cannot be overlooked. The isolation and distance from Earth could weigh heavily on settlers, making mental health an important consideration in the design of Mars habitats. Facilities for recreation, social interactions, and communication with loved ones back home will have to be incorporated to support emotional well-being. Despite these challenges, the vision of a human settlement on Mars continues to evolve. With every technological advancement and mission sent to explore the planet, we move a step closer to making this incredible dream a reality. Each challenge presents opportunities for ingenuity and resilience, paving the way for future generations to explore and perhaps call Mars home. Long-duration space travel will significantly transform the way we approach future missions in the cosmos. As we embark on journeys that stretch months or even years, we must confront a range of challenges that include not just technology, but also human biology and psychology. First, extended time in space affects the body in several ways. Astronauts experience changes such as muscle atrophy, bone density loss, and altered vision due to the absence of gravity. Addressing these issues will require innovative solutions like specialized exercise regimes and nutritional plans designed specifically for the space environment to maintain health. Moreover, long missions lead to new psychological challenges. The isolation of space and the confined living quarters can weigh heavily on crew members. Future missions will need to incorporate strategies for mental well-being, such as regular communication with loved ones back on Earth and recreational activities to foster a team spirit and alleviate stress. In terms of technology and equipment, we will likely carry more advanced life support systems. These systems should enable recycling of air and water for longer periods, reducing the need to bring large supplies from Earth. This change will not only make missions more sustainable, but also capable of supporting more crew members or longer stays. Further, the nature of exploration itself may shift. With longer missions, the focus could evolve from merely quick visits to a wider array of scientific research and sustainable living on other planets. Crews may stay longer on celestial bodies, allowing in-depth studies of environments, geology, and potential resources, like water ice on Mars or the moons of Jupiter, which could pave the way for future human settlement. As we enhance our capabilities for long-duration travel, we open the door to deeper exploration initiatives. A colony on Mars may become feasible, leading to a new chapter in our understanding of life beyond Earth. This will require collaboration across countries and disciplines as we all strive to overcome adversity and push the frontiers of human existence in space. The idea of sending humans to live on other planets raises important ethical questions that touch on a variety of issues. First and foremost, there is the question of responsibility. If we establish colonies on places like Mars or the Moon, we must consider the rights and welfare of potential life forms that may already exist there, even if they are microscopic. Disrupting an ecosystem, no matter how alien, could have unforeseen consequences. Next, we think about the individuals who would be sent on these missions. What does it mean for us to send people on long journeys to distant planets? These missions could be dangerous and would require participants to adapt physically and mentally to harsh environments. It's crucial to prioritize their safety and autonomy, ensuring that they are fully informed about the risks and challenges involved. Are we prepared to give them a voice in decisions that profoundly impact their lives? There's also the social and economic aspect to consider. Moving humans to another planet could create new forms of inequality and resource struggles. If these missions are funded by private corporations, will the benefits of living in space be accessible to everyone or just the wealthy few? Ensuring that the advancement of space colonization does not worsen inequality on Earth is a significant concern. Additionally, we must reflect on our motivations for venturing into the cosmos. Is the push for colonization driven by a genuine desire to expand human knowledge and experience, or is it a result of an escapism from Earth's problems? This introspection is essential as we set the stage for what may be the next chapter in human history. As we look to the stars, we must ground our ambitions in a careful consideration of ethics. Our responsibility extends beyond the technical challenges and includes a commitment to do no harm, respect all forms of life, and promote equity within our own species as we take these monumental steps toward becoming a multi-planetary civilization. Throughout the history of space exploration, there have been landmark achievements that have shaped our understanding of the universe and our place within it. One of the earliest milestones was the launch of a satellite known as Sputnik, which marked humanity's first venture into space. This event in the 1950s not only initiated the space race, but also opened the door to an era of scientific discovery. Following this, the first human in space, Yuri Gagarin, orbited Earth, demonstrating that humans could survive and function in outer space, further igniting public interest in space travel. The Apollo program reached a pinnacle with humans landing on the Moon. Neil Armstrong and Buzz Aldrin's footsteps left an indelible mark on this celestial body in 1969, showcasing not just our ability to reach the Moon, but also the potential to explore distant worlds. The exploration of Mars has also been a significant focus, with rovers such as Spirit and Opportunity providing unprecedented data about the Martian landscape and its history, revealing clues that suggest water once flowed on its surface. In more recent years, the Curiosity rover has continued this exploration, capturing captivating images and conducting experiments that hint at the planet's past habitability. Another groundbreaking accomplishment has been the development and maintenance of the International Space Station. This unique laboratory orbits our planet and serves as a cooperative venture among multiple nations. It allows for research in microgravity that leads to advancements in medicine, technology, and understanding the basic elements of biology. Exploration of our solar system expanded with robotic missions to gas giants and their moons. The Voyager spacecraft provided humanity's first detailed images of Jupiter, Saturn, and their moons, sending back data for over 4 decades. Recently, missions such as New Horizons brought us closer to the icy body known as Pluto, delivering fascinating information about its environment. As we continue to push boundaries with projects aiming to return humans to the Moon and eventually send crewed missions to Mars, each achievement builds upon the last, revealing the vast possibilities of space exploration. These endeavors not only enhance our scientific knowledge, but also inspire future generations to look to the stars and dream of what lies beyond our home planet. Modern telescopes have transformed our view of the universe, allowing us to see farther and clearer than ever before. These advanced instruments are designed to detect various types of light, from visible colors that our eyes can perceive to invisible wavelengths, such as infrared and ultraviolet. This diversity in observation expands our ability to study celestial objects that were once inaccessible. One major leap in telescope technology comes from the use of larger mirrors. A bigger mirror can collect more light, revealing fainter stars and distant galaxies. Imagine trying to see a candle from a distance in the dark. The more light you can gather, the clearer that flicker becomes. Similarly, larger mirrors help astronomers capture more light from the cosmos, enabling them to observe details they could never see with smaller, traditional telescopes. Another breakthrough is the use of adaptive optics. This technology corrects distortions caused by the Earth's atmosphere, which can blur images. Picture looking at a fish tank. If the water is still, you can see clearly, but if the water is moving, everything becomes wavy and distorted. Adaptive optics helps to clear the view, allowing astronomers to get sharp images of stars and other celestial bodies. Space-based telescopes play an essential role as well. By positioning telescopes beyond Earth's atmosphere, they are unaffected by weather or light pollution, conditions that can significantly hinder observations from the ground. Observatories like the Hubble Space Telescope have captured breathtaking images and provided vital data about everything from the life cycles of stars to the expansion of the universe. Moreover, modern telescopes are equipped with advanced computers and imaging technology. These tools can analyze data in real time, identifying celestial bodies and phenomena as they occur. This means scientists can track supernova explosions or monitor the behavior of asteroids much more efficiently than before. Modern telescopes enhance our understanding of the universe by allowing us to gather more light, correct for atmospheric interference, operate in the vastness of space, and utilize cutting-edge technology for data analysis. Together, these advancements are unlocking the secrets of the cosmos, helping us to unravel the mysteries of how the universe works. The International Space Station is like a floating laboratory that has revolutionized our understanding of various scientific fields. It provides a unique environment where research can be conducted in microgravity. This lack of gravity allows scientists to study physical processes that are difficult, if not impossible, to replicate on Earth. For instance, researchers have observed how fluids behave differently and how materials react when they are not influenced by gravity. One major area of study on the International Space Station is human health. Scientists conduct experiments to better understand how the human body adapts to long periods in space. This research helps us learn about the impacts of space travel on muscles, bones, and even the immune system. Understanding these changes is crucial, especially as we prepare for longer missions to destinations such as Mars. Life sciences are also a key focus. Scientists investigate how plants grow and develop in space. By growing plants in a microgravity environment, they can see how different factors, like light and nutrient availability, affect growth. This knowledge is vital for future space exploration, as it may provide insights into how we can produce food away from Earth. The International Space Station is also a platform for technology development. It serves as a testing ground for new technologies that can support future exploration missions. Innovations such as advanced life support systems and better radiation shielding are tested in this unique environment, ensuring that they function effectively in space. In addition, the station contributes to our understanding of fundamental physics. Experiments on the effects of radiation, cosmic rays, and other phenomena help researchers deepen their grasp of the universe and our place within it. This research has practical applications too, such as improving satellite technology and understanding climate change through observations of the Earth. Lastly, the International Space Station fosters international collaboration. Scientists from various countries work together, sharing knowledge and resources. This spirit of cooperation not only advances scientific discovery, but also promotes peace and unity in the quest for knowledge about our universe. The International Space Station serves as an invaluable resource for scientific advancement, offering insights that impact health, agriculture, technology, and our broader understanding of the cosmos. Robotic missions play a crucial role in exploring distant worlds, pushing the boundaries of our understanding of the universe. Unlike human missions that require life support and safety measures, robotic explorers can travel to places where humans cannot yet venture due to harsh conditions or great distances. These missions enable scientists to gather valuable data without the limitations and risks associated with human travel. For example, robotic spacecraft can survey the surfaces of other planets, capturing detailed images and measurements. They can analyze the composition of soil and rocks, searching for signs of water or other elements that are vital for life. The findings from these explorations help researchers learn about the geological history of these worlds and their potential for habitability. Furthermore, robotic missions can be equipped with a variety of scientific instruments, enhancing their ability to conduct experiments and collect data. For instance, rovers that traverse the surface of Mars can carry laboratory tools to conduct chemical tests directly on Martian soil. This provides real-time results and insights that would be difficult to achieve through remote observation alone. Robotic missions also enable us to study extreme environments that resemble those found in outer space. By simulating conditions on moons like Europa or celestial bodies like Titan, scientists can test theories about how life might arise beyond Earth. Ultimately, these machines advance the frontiers of our knowledge, paving the way for future human exploration and helping us understand our place in the cosmos. As we look to the future of space exploration, several upcoming missions are set to change our understanding of the universe profoundly. One of the most exciting endeavors is the Artemis program, planned by NASA, which aims to return humans to the moon by landing astronauts on its surface for the first time in more than half a century. This mission's goal isn't just to explore, it's about setting up a base for future missions to Mars, allowing us to study lunar resources and test technologies that will support deeper space travel. Another critical mission on the horizon is the James Webb Space Telescope, designed to explore the cosmos in unprecedented detail. Unlike its predecessor, the Hubble Space Telescope, this new observatory will primarily observe infrared light, allowing it to peer through clouds of gas and dust, exploring the early universe and possibly even identifying the atmospheres of exoplanets. The data it collects could offer significant insights into the formation of stars, galaxies, and even the potential for life beyond Earth. Additionally, the European Space Agency is preparing the Jupiter Icy Moons Explorer, known as JUICE. This spacecraft will study 3 of Jupiter's largest moons, Ganymede, Europa, and Callisto. Each of these moons is believed to harbor subsurface oceans, making them essential targets in the search for extraterrestrial life. By understanding their environments and geology, we could unlock clues about the conditions that might support life beyond our planet. Finally, private companies like SpaceX and Blue Origin are advancing rapidly with their missions and technologies. SpaceX's Starship aims to facilitate human travel to Mars, supporting an ambitious vision of creating a sustainable human presence on the Red Planet. This pioneering path could reshape humanity's role in exploring and potentially colonizing other worlds. These missions reflect our relentless pursuit of knowledge and our desire to expand humanity's reach beyond Earth. Each one promises to deliver new discoveries, deepen our understanding of the cosmos, and perhaps even answer some of the most profound questions about life, our place in the universe, and the future of our species. advanced propulsion systems are reshaping the future of manned space travel in remarkable ways. Traditionally, rockets rely on chemical propulsion, which is powerful but limited in both speed and efficiency. Imagine trying to escape a deeply entrenched gravitational well while carrying only a specific amount of fuel. This has long dictated how far we could go and how quickly we could reach our destinations. Now, consider advanced systems like ion drives or plasma propulsion. These methods work by using electricity to accelerate ions or plasma, creating a continuous, efficient thrust that operates much differently than conventional rockets. With these engines, spacecraft can sustain longer journeys without needing to carry massive amounts of fuel. This means we could reach destinations like Mars or even the outer planets in less time, opening the door to more ambitious missions. Another groundbreaking concept is nuclear thermal propulsion, which uses heat generated from nuclear reactions to propel spacecraft. This technology can produce impressive thrust and is significantly more efficient than chemical engines. Plus, it can reduce travel times for crewed missions, minimizing the risks associated with long-duration spaceflights, such as exposure to radiation and the psychological challenges of isolation. Even more futuristic possibilities lie in concepts like antimatter propulsion. While it is still theoretical, antimatter could produce enormous amounts of energy, leading to speeds close to that of light. This would make interstellar travel conceivable, sparking dreams of reaching other star systems within a human lifetime. As we advance these technologies, the boundaries of human exploration are expanding. Manned missions could stretch beyond our moon and into the depths of our solar system and beyond. With each evolution in propulsion, we not only change how fast we can travel, but also redefine what humanity can achieve in the vastness of space. In recent years, private companies have dramatically changed the landscape of space travel. Traditionally dominated by government agencies, such as NASA and the Russian space program, the entry of commercial enterprises has introduced new ideas and technologies. This dynamic shift has made space exploration more feasible, affordable, and innovative. Take the work of SpaceX as an example. Founded by Elon Musk, this company has disrupted the launch market by developing reusable rockets. This approach allows the same rocket to be launched multiple times, significantly reducing costs and enabling more frequent missions. As a result, launching payloads into space has become cheaper than ever before. They have also made headlines by relocating cargo to the International Space Station, demonstrating the capability for private entities to partner with government space programs. Another noteworthy player is Blue Origin, founded by Jeff Bezos. This company aims to make space travel accessible to everyone, not just astronauts. Their New Shepard rocket is designed for suborbital flights, offering civilians the chance to experience a few minutes of weightlessness. This focus on tourism reflects a growing interest in making space a destination for leisure, not just research. Beyond mere transportation, these companies have driven technological advancements. There's a strong emphasis on innovation and competition that encourages rapid development. For example, projects like the Mars colonization plans initiated by SpaceX introduce ambitious visions that inspire global interest in science and engineering. Furthermore, private companies have fostered collaborations that pool resources and expertise. Partnerships between private firms and governmental bodies have led to improved missions and expanded capabilities. This collaboration is crucial for larger projects like building lunar bases and facilitating human missions to Mars. The influence of private companies on space travel has been transformative. By introducing cost-saving technologies, expanding access to space, and fostering a competitive environment, they have opened up new possibilities for exploration. This new era not only redefines how we venture beyond our planet, but also sets the stage for an exciting future in space travel. Space is full of wonders, but it also harbors a variety of threats to life on Earth. One of the most notable dangers comes from asteroids and comets. These celestial bodies, sometimes traveling at incredibly high speeds, can collide with our planet. Such impacts can cause catastrophic events, leading to massive destruction. Historically, these cosmic collisions have been linked to the extinction of species, including the dinosaurs. Another significant risk is solar flares. Our sun periodically releases bursts of energy and particles into space. When these solar flares are directed towards Earth, they can disrupt communications and navigation systems and even affect electrical grids. In extreme cases, a powerful solar storm could result in widespread power outages, disabling the technology we rely on daily. In addition, cosmic radiation is a constant presence beyond our atmosphere. While Earth's atmosphere and magnetic field provide substantial protection, astronauts in space and high-altitude flights are at greater risk. This type of radiation can damage living cells and increase the chance of cancer and other health issues. Lastly, space debris poses a growing threat. As we send more satellites and equipment into orbit, remnants from past missions, like defunct satellites and discarded rocket parts, accumulate. This floating trash can collide with operational satellites, causing failures or accidents that can impact our daily lives. While space offers many opportunities for exploration and knowledge, it also presents real dangers that require continuous monitoring and preparation to safeguard life on Earth. Scientists track and predict the impact of asteroids using a combination of advanced technology, observational techniques, and mathematical modeling. The journey begins with powerful telescopes that survey the skies, monitoring the vast expanse for new asteroids and tracking those already known. When an asteroid is detected, its position is recorded at various times to understand its orbital path around the Sun. Next, scientists calculate the asteroid's orbit, which requires determining its speed and direction. This is done by observing how the asteroid moves against the background stars over time. With this information, they use mathematical formulas to predict where the asteroid will be in the future. The accuracy of these predictions improves as more data is collected over time, allowing scientists to refine their understanding of the asteroid's trajectory. Additionally, many observatories around the world and some space-based missions work together to share data. This collaboration enhances the detection and tracking process. When models suggest an asteroid may come dangerously close to Earth, scientists calculate the potential impact risk. They analyze various scenarios, including the asteroid's size and speed, to estimate the consequences of an impact should it occur. In some cases, if an asteroid is deemed a potential threat, scientists propose mitigation strategies. This could involve changing its path using spacecraft or, at the very least, preparing for the impact. Through continued observation and research, scientists aim to protect our planet, ensuring they have the tools and knowledge to respond should a significant asteroid ever threaten Earth. Protecting Earth from cosmic impacts is a crucial area of research and innovation. Scientists have been exploring several promising methods to address the potential threat posed by asteroids and comets. One approach involves detecting these objects early, allowing us to track their paths in space. By using powerful telescopes and radar systems, astronomers aim to discover and monitor any near-Earth objects, identifying those that might pose a risk. Once a potential threat is identified, various strategies come into play. One method is known as the kinetic impactor technique. This involves sending a spacecraft to collide with an asteroid at high speed. The impact could change the asteroid's trajectory, nudging it onto a safer path away from Earth. Think of it as gently tapping a bowling ball to alter its course on the lane. Another method is the gravitational tractor approach. In this technique, a spacecraft would hover near the asteroid for an extended time. The spacecraft's gravitational pull could gradually alter the asteroid's orbit, steering it away from a collision course without the need for a direct impact. Additionally, scientists are investigating using nuclear devices. The idea would be to detonate a nuclear explosion near an asteroid, producing a powerful force that can either break it apart or change its trajectory significantly. This method is often seen as a last resort, primarily due to the risks and complexities involved. International collaboration is key in this endeavor. Many nations are sharing data and resources to create a comprehensive response plan. Continuous monitoring, advanced technology, and community awareness are essential components of protecting our planet from cosmic impacts. By developing these methods, we aim to ensure a safer future against the vast uncertainties of space. Space weather refers to the environmental conditions in space influenced by the sun's activity, particularly during events like solar flares and coronal mass ejections. When the sun releases energy and charged particles into space, it can interact with Earth's magnetic field and atmosphere, leading to various effects that can impact both technology and everyday life. One of the most significant influences of space weather is on communication systems. Satellites, which provide vital services for everything from GPS navigation to television broadcasts, can be disrupted by these charged particles. Imagine trying to listen to your favorite radio station during a thunderstorm. Similarly, increased solar activity can lead to radio waves becoming distorted or completely blocked, making communication difficult. Moreover, electrical systems on Earth can experience disturbances. High altitudes, like those found at power stations, are particularly vulnerable to changes caused by geomagnetic storms. These storms can induce electrical currents in long power lines, potentially leading to transformer failures or even widespread electrical outages. It's similar to how a sudden surge of water can overwhelm a dam, potentially causing it to fail. Not just technology, but even our health can be affected. Astronauts in space, for instance, are at risk of exposure to increased radiation during solar storms, which can be harmful over time. On the ground, however, the atmosphere acts as a protective shield. Yet, during intense solar events, increased radiation can also lead to beautiful phenomena like the auroras, making the night sky shine with colors as charged particles collide with gases in our atmosphere. Lastly, space weather affects navigation systems. High-frequency radio signals can be affected, which might confuse pilots and maritime navigators. Think about trying to use a compass during a storm. It can lead you off course if the magnetic field shifts unexpectedly. Space weather poses a variety of threats to our technology and everyday lives, reminding us of the powerful connection between our planet and the cosmos. As we continue to advance technologically, understanding and preparing for these cosmic events becomes increasingly important. Space debris poses significant challenges for future space missions, and its implications cannot be overlooked. As humanity continues to explore and utilize space, the remnants of past missions, defunct satellites, and even fragments from spacecraft collisions are accumulating in Earth's orbit. This debris travels at incredibly high speeds, making even small pieces potentially catastrophic. Imagine if a tiny ball were to collide with a speeding car, the effect can be disastrous. Similarly, a small piece of space debris can penetrate and damage working spacecraft, satellites, or the International Space Station. Each year, the number of satellites and equipment in orbit increases, escalating the risk of collision. Even a minor incident can lead to the creation of more debris, creating a cycle known as the Kessler syndrome, where the density of objects in low Earth orbit could reach a point where collisions become commonplace, making parts of space nearly unusable. For future missions, this debris threat means that space agencies and private companies must develop sophisticated tracking systems to monitor and predict the paths of debris. Mission planners need to devise strategies to either dodge potential collisions or minimize risks. Such preparations may involve changing the trajectory of spacecraft, which requires additional fuel and resources. Moreover, designing spacecraft that can withstand impacts from debris becomes a priority, contributing to increased costs and engineering challenges. Innovation is key in addressing this problem. Researchers are exploring ways to actively remove debris from orbit, utilizing nets, harpoons, or other technologies that could capture and deorbit defunct satellites. International cooperation is also essential, as space knows no borders. The challenge of space debris requires a united approach to ensure the safety and sustainability of our ventures beyond Earth. As we look towards the future of space exploration, dealing with space debris will shape how missions are planned, designed, and executed. Finding effective solutions will be crucial to safeguard not just current operations, but also the exploration of deeper space, ensuring that humanity can continue its journey among the stars. Researchers are keenly aware of the Sun's powerful influence on Earth, particularly when it comes to solar radiation. To study its long-term effects, scientists employ a combination of satellite observations, ground-based instruments, and computer models. First, satellites orbiting our planet monitor solar activity in real time. These satellites capture data on solar flares and sunspots, allowing researchers to track changes in radiation. By observing how these solar events correlate with climatic shifts over time, scientists can start to understand the relationship between the Sun's behavior and Earth's weather patterns. Ground-based instruments play a vital role too. These tools, placed in various environments, measure the amount of solar radiation reaching the Earth's surface. They monitor changes over decades, providing a wealth of data about potential trends and long-term impacts on ecosystems and human activities. Moreover, paleoclimatology, the study of past climates, gives researchers insights into how solar radiation affected Earth long before modern instruments. By examining ice cores, tree rings, and sediment layers, scientists can infer periods of increased solar activity and their effects on ancient climates. Lastly, computer models simulate different scenarios based on existing data. By inputting various solar radiation levels, scientists can predict potential future impacts on climate. These models help researchers explore how changing solar conditions may affect temperature, weather patterns, and even atmospheric chemistry. By combining direct measurements with historical data and sophisticated modeling, researchers are piecing together the complex puzzle of solar radiation's long-term effects on our planet. This knowledge is crucial in preparing for future climate scenarios influenced by solar activity. Scientists are actively exploring ways to address potential threats from nearby supernovae, which are powerful explosions marking the death of a massive star. The first step in this mitigation process is closely monitoring the sky for signs of such celestial events. Astronomers use advanced telescopes and observation methods to track the locations and activities of stars that might go supernova, especially those close enough to have an impact on Earth. One key aspect is understanding which stars are at risk of exploding. By studying the characteristics of these stars, such as their size, age, and composition, researchers can identify those that may enter a supernova phase more imminently. This involves not only observing their light emissions, but also using models that predict stellar evolution. In addition, scientists are educating the public and the scientific community about the potential effects of a supernova nearby. A supernova explosion could emit harmful radiation and create energetic particles that might affect our atmosphere and biosphere. Knowledge is power, and understanding these risks allows us to prepare better and react more effectively. Should a supernova occur relatively close to Earth, scientists also study ways to fortify our atmosphere against potential harmful radiation. This can involve enhanced monitoring of cosmic radiation levels and developing better models to predict and understand atmospheric responses to such cosmic events. Through a combination of monitoring, education, and research, scientists are taking important steps to ensure that we are prepared for any potential threats posed by nearby supernova, aiming to protect our planet and its inhabitants from unexpected cosmic disruptions. The search for extraterrestrial life centers around several key objectives that drive scientists and researchers. First and foremost, the primary goal is to discover any form of life beyond Earth, whether it be simple microorganisms or advanced civilizations. This involves exploring environments within our own solar system, like Mars or the icy moons of Jupiter and Saturn, where conditions might support life. Another major objective is to understand the conditions necessary for life to arise. Scientists study extreme environments on Earth, such as deep-sea vents or polar regions, to learn how life can adapt and thrive. This knowledge helps to broaden our understanding of where else in the universe life might exist. Additionally, the search involves looking for biosignatures, distinctive signs of life on distant exoplanets. These might include specific chemical signatures in a planet's atmosphere or unusual patterns on its surface. Telescopes designed to analyze light from these distant worlds play a crucial role in this part of the mission. Communication is another forefront objective. Researchers are actively listening for signals from intelligent civilizations. This includes monitoring radio waves and other forms of transmissions that could indicate advanced technology elsewhere in the universe. Ultimately, the pursuit of understanding whether we are alone in the universe has profound implications for humanity. It challenges our perspectives on life, our existence, and our place in the vast cosmos, making each step in this quest crucial for uncovering the mysteries of life itself. Scientists use radio signals as a way to listen for possible communications from extraterrestrial civilizations. The idea rests on the principle that radio waves, which are a type of electromagnetic radiation, travel through space much faster than sound waves do. This quality allows them to cover vast distances, making them ideal for interstellar communication. To search for alien signals, scientists focus on specific regions of the radio spectrum that are less likely to be filled with natural cosmic noise. They choose frequencies that are unique and could stand out, indicating a deliberate transmission rather than random noise created by natural phenomena like stars or planets. One of the most famous frequency ranges studied is the one known as the water hole, which lies between the frequencies emitted by hydrogen and hydroxyl molecules, two of the most abundant substances in the universe. This range is thought to be a logical choice for any intelligent life trying to reach out. Radio telescopes are their primary tools for detection. These large, dish-shaped antennas are designed to capture radio waves from space. They can track signals over time and record any unusual patterns that appear. When a radio signal is detected, scientists analyze it for characteristics that would suggest it is artificial. For example, if the signal is narrowband, meaning it occupies a very small range of frequencies, it is more likely to be intentional rather than something natural. Once a potential signal is identified, researchers conduct follow-up observations to confirm its source. They look for patterns or repeated bursts that might indicate a signal is not just a one-time event. If they find that the signal comes from a specific direction in the sky and is consistent, it raises the excitement about the possibility that it could be a communication from an intelligent civilization. However, the search is filled with challenges. The vastness of space means many signals could easily be missed, and distinguishing between artificial signals and natural background noise is not straightforward. Yet, with each advance in technology and analysis techniques, scientists continue their quest, fueled by the hope of discovering that we are not alone in the universe. The search for signs of life beyond Earth has captivated scientists and enthusiasts alike, focusing on various intriguing clues across different celestial bodies. One of the most notable discoveries comes from Mars, where evidence of ancient riverbeds and minerals that typically form in water suggests that the planet once had liquid water on its surface. The presence of methane gas in the Martian atmosphere has also raised eyebrows. On Earth, methane is often produced by living organisms, though it can also have non-biological origins. Moving further out, one of the moons of Jupiter, Europa, has become a focal point due to its icy crust covering a vast, potentially subsurface ocean. This ocean could create conditions similar to those found in some of Earth's deepest oceans, where life thrives around hydrothermal vents. Scientists are eager to explore Europa further to see if it harbors any signs of living organisms. In our exploration of Saturn's moon, Enceladus, researchers found geysers spewing water vapor and organic molecules into space, creating a compelling case for the existence of a subsurface ocean. This ocean, along with the detected organic compounds, may provide the necessary ingredients for life. Beyond our own solar system, astronomers are analyzing exoplanets, planets orbiting other stars. Some of these planets lie within their stars' habitable zones, where conditions might be just right for liquid water to exist. The detection of specific atmospheric gases, such as oxygen and carbon dioxide, could indicate biological processes similar to those on Earth. further igniting discussions about the potential for life beyond our home planet. These signs, from microbial-like activity in Mars' atmosphere to the exciting possibilities of frozen moons harboring oceans, form a patchwork of research that propels our understanding of where and how life might exist in the vastness of the universe. Each discovery adds a piece to the puzzle of life's potential in locales once thought to be uninhabitable. Studying extremophiles, organisms that thrive in Earth's most extreme environments, plays a crucial role in the quest for alien life beyond our planet. These remarkable creatures can be found in places that seem inhospitable to most life forms, such as intense heat sources like hydrothermal vents, highly acidic lakes, or the frigid conditions of Antarctica. By understanding how these organisms survive and adapt to challenges like extreme temperatures, high radiation levels, or lack of oxygen, scientists gain valuable insights into the potential for life elsewhere. When exploring other planets and moons in our solar system, scientists look for environments that might mirror those extreme conditions on Earth. For example, the icy surface of Europa, one of Jupiter's moons, is believed to have a subsurface ocean, potentially harboring life. Examining how extremophiles manage to exist in similar environments gives researchers clues about what life-supporting conditions might look like in these alien worlds. By identifying the biological processes these organisms use to thrive, we can form hypotheses about how life might adapt in the unique and varying conditions found in outer space. Additionally, studying extremophiles fuels the development of technology and models for exploration missions. If we can replicate the qualities that allow these organisms to survive harsh environments here, we enhance our chances of detecting or even modeling life on other planets. These findings inform our approaches to astrobiology, guiding missions that seek signs of life by focusing on regions that share similar characteristics to Earth's extremophiles' habitats. Thus, through the lens of extremophiles, we expand our understanding of life's resilience and adaptability, paving the way for exciting discoveries about life beyond Earth. The discovery of extraterrestrial life would fundamentally transform human society in profound ways. First, it would shift our understanding of our place in the universe. For centuries, humans have pondered their uniqueness in a seemingly vast and empty cosmos. Finding life beyond Earth would challenge this notion, suggesting we are not alone and that life can arise in various forms throughout the universe. Culturally, this revelation could lead to a rethinking of our philosophies and religions. Many belief systems might need to adapt to incorporate the idea of other sentient beings and their potential histories. Conversations about morality and ethics would become more complex as we consider the rights of non-human intelligences. This could foster a sense of unity among people on Earth, as the shared experience of identifying with a broader cosmic community could overshadow our existing divisions. In terms of science and technology, the search for life beyond our planet might accelerate advancements. We could see ambitious new explorations across the solar system and beyond, pushing our technological boundaries. This pursuit might also inspire collaborations across nations, as shared goals in space exploration would encourage teamwork among various cultures. Additionally, the discovery could influence our approach to the environment here on Earth. Recognizing the fragility of life, whether on our planet or elsewhere, could lead to an increased emphasis on sustainability practices and the protection of our own ecosystem. Societal structures could also shift. Educational perspectives might change, with a greater focus on astrobiology and anthropology of potential extraterrestrial cultures. Governments could alter their policies to account for planetary defense and the potential need for international guidelines regarding our interactions with extraterrestrial life. Overall, the discovery of extraterrestrial life would act as a catalyst for humanity to reflect, adapt, and possibly evolve, fostering a deeper understanding of our existence and potential as a species. It would not just be a scientific milestone, but a turning point that redefines human identity and our long-term goals as we navigate the cosmos. International collaborations play a vital role in the quest to find life beyond Earth by bringing together diverse expertise, resources, and perspectives. When countries share their knowledge, they can tackle complex challenges more effectively than any one nation could alone. For instance, different countries may provide unique technologies or scientific insights that combine to create more advanced exploration tools. Working together also means pooling financial resources, allowing for larger and more ambitious missions that would be difficult for a single country to fund. This collaborative approach enables teams to send powerful telescopes into space, build sophisticated rovers for distant planets, or develop advanced instruments that can analyze samples for signs of life. Moreover, international partnerships foster a sense of shared purpose and encourage the free exchange of ideas. Scientists from various backgrounds may propose innovative theories or methodologies that they wouldn't have conceived in isolation. This cross-pollination of ideas often leads to breakthroughs that accelerate the search for extraterrestrial life. Additionally, joint missions can increase public interest and support for space exploration. When countries come together for a common goal, it captures the imagination of people worldwide. This unity sends a powerful message that the search for life beyond our home planet is a shared human endeavor, reinforcing the idea that we are all in this together. Finally, collaboration can help standardize data collection and analysis methods across different countries, making it easier to compare findings from various missions. By creating a unified approach, scientists can build on each other's work and strengthen the overall understanding of what is needed to detect life in the cosmos. International partnerships enhance every aspect of the search for extraterrestrial life, making the pursuit more comprehensive, efficient, and exciting. The potential discovery of extraterrestrial life raises profound ethical questions that touch upon various aspects of humanity, science, and our place in the universe. Initially, there is the concern about how we would treat known life forms from other planets. If these beings exhibit signs of intelligence, what rights would they possess? Should they be treated with respect and dignity, similar to how we understand the rights of human beings? Additionally, there are environmental ethical considerations. If we were to discover microbial life on a distant planet, our actions could threaten its habitat. The principle of preserving ecosystems applies not only to Earth, but also to other worlds. We must consider the implications of our exploration efforts, ensuring that our search for knowledge does not lead to contamination or destruction of these potentially fragile environments. There is also the matter of exploring the motivations behind seeking other life forms. Are we driven by curiosity, fear, or the desire for colonization? If extraterrestrial life is found, how do we prevent humanity's historical mistakes, such as exploitation or domination, from repeating themselves on an interstellar scale? The lessons learned from our own history with colonization and indigenous populations need to guide our approach to any new entities we may encounter. Another significant aspect involves the societal impact of such a discovery. How would it change our perceptions of ourselves? The realization that we are not alone could shift philosophical and religious perspectives, leading to new narratives about life and existence. Finally, the ethical dialogue must include how we approach communication with extraterrestrial beings, ensuring our intentions are transparent and peaceful. Creating a framework that prioritizes cooperation and respect is essential, allowing for an open and responsible exploration of this monumental potential. The search for extraterrestrial life is not only a quest for understanding the cosmos, but also a critical journey into understanding our moral responsibilities. Throughout history, ancient cultures have looked up at the night sky and found meaning in the movements of celestial bodies and phenomena. For these civilizations, the stars, planets, and natural events often held profound significance, influencing their beliefs, traditions, and practices. Many ancient societies saw celestial bodies as deities or spirits. For example, the Egyptians worshipped the sun and associated it with their gods, believing that its daily journey across the sky reflected the cycle of life and death. They constructed grand monuments aligned with the sun to celebrate this connection. Similarly, the Maya meticulously tracked the movements of celestial objects and incorporated these observations into their ceremonial calendar, linking agricultural activities with astrological events. In other regions, such as Mesopotamia, people observed the cycles of the moon and planets and created one of the earliest forms of astronomy. They assigned names to different constellations, envisioning stories and mythical beings within the patterns they saw. Their understanding of these celestial patterns allowed them to predict seasonal changes, guiding agricultural practices crucial for survival. The ancient Greeks were also pivotal in shaping celestial interpretation. They developed models of the universe that explained the apparent movements of the planets, stars, and the sun. Their philosophical notions that celestial bodies governed earthly affairs led to astrological practices which suggested that the position of celestial bodies could influence human fate. Across the globe, indigenous cultures, like the Aborigines of Australia, also recognized important connections between their land, cultural stories, and the cosmos. They used the night sky as a map for navigation and a calendar for seasonal changes, deeply entwining their identity with the celestial realm. Ancient cultures viewed celestial bodies not merely as physical entities, but as integral components of their belief systems. The night sky served as a canvas for storytelling, a tool for tracking time, and a guide for understanding the universe and their place within it. The cosmic perspective fundamentally shifts how we view ourselves and our place in the universe. Imagine standing on a mountain and looking out over a vast landscape. You can see far and wide, gaining insight into your surroundings. Now, think of that mountain as the Earth and the landscape as the cosmos. When we gaze up at the night sky, filled with myriad stars and galaxies, it can trigger a profound sense of connection to something much larger than ourselves. This perspective nurtures a sense of humility. In the grand scheme of the universe, our individual lives, struggles, and aspirations can seem quite small. It reminds us that our planet is just a tiny speck in a vast ocean of space. This realization often leads to a deeper appreciation for our environment and emphasizes the importance of caring for our home, Earth. Furthermore, contemplating the vastness of space can spark existential questions. Are we alone in this universe? What is the significance of our existence? These inquiries can encourage a collective search for meaning beyond the confines of our immediate experiences. Philosophically, this might lead individuals to embrace broader ideas of unity, diversity, and shared human experience. In addition, the cosmic perspective can dilute feelings of separation. Recognizing that we share this planet with billions of others, and possibly with life elsewhere, can foster a sense of kinship among us. Humans begin to see themselves not as isolated entities, but as part of a larger community. The cosmic perspective expands our philosophical outlook by promoting humility, sparking deep questions about existence, enhancing our connection to one another, and encouraging a sense of responsibility for our planet. This shift can help guide our actions and aspirations as we navigate life on this remarkable blue dot in a vast universe. Throughout history, humanity's fascination with the stars and the vastness of space has given rise to a rich tapestry of myths and legends. Ancient civilizations often looked to the night sky and saw not just distance, but meanings, stories, and gods. For instance, many cultures created tales about constellations. The Greeks, for example, told elaborate stories about the characters represented by the stars, such as Perseus and Andromeda, illustrating heroism and adventure. In various Native American cultures, the stars were seen as ancestors watching over the Earth. The Milky Way, in particular, was often referred to as a celestial river, symbolizing guidance and the journey of life. Such stories helped explain natural phenomena or offered moral lessons, linking human experience with the cosmos. The myths of celestial bodies also reflect humanity's attempt to understand the universe. The planet Venus, often called the morning star, has been associated with different deities around the world. In some cultures, it represented love and beauty, while in others, it was a harbinger of war. This duality speaks to our awareness of cycles, both in nature and human emotions. As technology advanced, the mythological interpretations began to evolve. With the advent of space exploration, new myths emerged around the idea of extraterrestrial life. These narratives involve tales of alien contact, often shaped by our hopes and fears about other beings. Films and literature began to imagine vast civilizations out there, igniting curiosity about what life might be like beyond Earth. The idea of cosmic beings and advanced intelligence plays into our longing for connection and understanding of our place in the universe. Science fiction became a modern myth, weaving together these themes of exploration and the unknown. Stories of brave astronauts venturing into the unknown resonate with the ancient tales of heroes embarking on epic quests, reinforcing humanity's enduring desire to explore and understand the mysteries of space. These myths and legends, whether ancient or modern, offer insight into how humanity interacts with the cosmos. They reflect both our awe of the universe and the deep questions we have about existence, life, and our future among the stars. Space exploration has left an indelible mark on modern culture and art, shaping not only our scientific understanding, but also our creative expressions. The quest to reach the stars has inspired countless artists, writers, filmmakers, and musicians to delve into themes of exploration, humanity, and the unknown. In literature, the genre of science fiction blossomed alongside the advancements in space travel. Authors imagined worlds beyond our own, exploring profound questions about existence and the future of humanity. These narratives often reflect our hopes and fears regarding technology and the infinite universe, influencing how we think about our place in it. Visual arts have also embraced the cosmos. Artists use the imagery of planets, stars, and galaxies to evoke awe and wonder. Space-themed exhibitions at galleries and museums showcase works that capture the beauty and mystery of outer space, often inspiring people to contemplate the larger questions of life and existence. The famous blue swirls and swirling stars in abstract paintings draw directly from the vastness of the universe, creating a visual dialogue between art and science. Film and television have played significant roles in popularizing space exploration. Movies like Star Wars and Interstellar not only entertain, but also provoke thought about the nature of time, space, and our future as a species. These stories resonate with audiences, sparking interest in real scientific endeavors and encouraging future exploration. They create a cultural backdrop where the possibilities of space travel feel tangible and within reach. Moreover, music has been deeply influenced by the themes of space. Composers and musicians create works that reflect the emotional landscape of exploration. From classic scores that accompany space documentaries to modern electronic music that evokes the ambience of otherworldly landscapes, the sounds of space resonate through our culture. The influence of space exploration also reflects in educational content and trends in technology. As people become more fascinated by the universe, science programs for children integrate these concepts into learning, fostering a generation curious about science and technology. Space exploration has seeped into every corner of modern culture and art, inspiring creativity and deepening our understanding of our universe. It continuously pushes the boundaries of artistic expression and encourages us to envision a future that extends beyond our planet, fostering a culture of curiosity and imagination. Space has always been a source of wonder and curiosity, filled with many enduring mysteries that pique human imagination. One of the most captivating is the enigma of dark matter. While we can see stars and galaxies, most of the universe is made of invisible material that does not emit light or energy. This dark matter interacts with regular matter through gravity, shaping galaxies and holding galaxy clusters together. The thought that most of the universe is composed of something we can't see or fully understand sparks endless questions about what lies beyond our perception. Another fascinating mystery is dark energy. This mysterious force seems to be responsible for the accelerating expansion of the universe. It's like an invisible hand pushing galaxies apart, and it raises questions about the fate of the universe. Will it continue to expand forever, or will it someday collapse back in on itself? This uncertainty leads us to ponder the origins and future of everything we know. Additionally, the concept of black holes continues to intrigue people. These regions of space exert such strong gravitational forces that not even light can escape. Understanding what happens inside a black hole, particularly regarding the fate of objects that cross its boundary, stirs imaginations. Do they lead to another universe, or are they simply cosmic traps? Life beyond Earth remains one of the most enduring mysteries. The idea that microorganisms or even intelligent beings might exist elsewhere in the universe challenges our understanding of life itself. Scientists explore extreme environments on Earth to look for clues about how life might survive on other planets or moons, like the icy surface of Europa, one of Jupiter's moons. Then there's the question of time and space interaction. The nature of time fascinates us. Is it linear, or could it be more complex? Theories about time travel and alternate realities push the boundaries of our understanding, igniting imaginations about possibilities that could stretch far beyond our current capabilities. All these enduring mysteries of space connect our past, present, and future to something much larger than ourselves, inviting exploration and contemplation about the universe and our place within it. Each unanswered question invites further investigation, ensuring that the allure of space will continue to captivate generations to come. Religions and spiritual beliefs have long intertwined with our understanding of the cosmos. Throughout history, people have looked up at the night sky and wondered about their place in the universe, leading to diverse interpretations and teachings. Many ancient cultures viewed celestial bodies, the sun, moon, and stars, not just as physical entities, but as deities or sacred symbols. For them, the movements of these celestial objects guided agricultural practices, informed calendars, and shaped mythologies. In numerous spiritual traditions, the cosmos is often seen as a reflection of a greater order. For instance, some belief systems propose that the universe follows a divine plan, where each star and planet has significance in the context of creation and the human experience. This can foster a sense of connection between individuals and the larger universe, suggesting that humans are a part of a vast, interconnected web of existence. Religions often use the cosmos to express profound concepts. In many traditions, the idea of the heavens reflects a place of peace and communion, contrasting with the earthly realm of struggle and imperfection. This notion can lead to rituals or prayers that acknowledge the cosmos, inviting a spiritual presence to take part in human affairs. In Eastern philosophies, such as Hinduism and Buddhism, the cosmos is often viewed through the lens of cycles and interconnectedness. The concept of cycles, such as the cycles of life and rebirth, parallels celestial movements like the changing of seasons or lunar phases. Such ideas emphasize the belief in a continuous flow of time and existence, underscoring the unity that exists within the larger universe. In modern times, some spiritual movements and New Age beliefs incorporate scientific concepts, such as the Big Bang or the vastness of the universe, into their frameworks. They see the cosmos not only as a physical space, but as a canvas for exploring the nature of consciousness and existence itself. This integration of science and spirituality encourages people to explore profound questions about life, purpose, and the universe's mysteries. Overall, the cosmos serves as a powerful symbol in many religions and spiritual practices, providing a backdrop to understand existence, morality, and the divine. It invites believers to reflect on their place in a larger context and fosters a sense of wonder about the mysteries that lie beyond our earthly experience. The exploration of space represents a deep-rooted human desire to understand the unknown. Throughout history, people have looked up at the sky and wondered what lies beyond our planet. This curiosity drives us to seek answers, pushing the boundaries of our knowledge. Humans have an innate urge to explore, much like our ancestors who ventured into new lands across oceans. Space exploration is an extension of that same spirit. It's about venturing into vast, unexplored territories where no human has set foot. The quest to discover new worlds and understand the universe taps into our need for adventure and knowledge. Moreover, space exploration has the potential to answer big questions about our origins. Where did we come from? Are we alone in the universe? These questions fuel scientific research and inspire new generations of thinkers and dreamers. Learning about celestial bodies, like planets and stars, helps us understand not just the universe, but also our own planet and its place within it. Additionally, space exploration propels technological advancements. Many innovations that benefit our everyday lives, such as satellite technology and materials science, were developed through the challenges of exploring space. With these advancements, we also address pressing issues on Earth, like climate change and resource management. Ultimately, the exploration of space reflects our collective ambition to not only address the mysteries that surround us, but also to better ourselves as a species. It symbolizes hope, unity, and the relentless pursuit of knowledge that defines what it means to be human. Every step we take into the cosmos is a step towards a brighter future, one filled with possibilities we have yet to imagine. The planets in our solar system each have unique characteristics that make them distinct. Starting with the inner planets, which are small and rocky, we have Mercury, the closest planet to the Sun. It has an extremely thin atmosphere and temperatures that swing dramatically between scorching heat and freezing cold. Next is Venus, often seen as Earth's twin due to its similar size, but its thick, toxic atmosphere creates a runaway greenhouse effect, making it the hottest planet in our solar system. Earth, our home, stands out because it is the only planet known to support life. It has a breathable atmosphere and a perfect balance of water, land, and temperature. Mars, known as the Red Planet, captures attention with its rusty color from iron oxide on its surface and features like the tallest volcano and the deepest canyon in the solar system. As we move to the outer planets, we enter a realm of gas giants and ice giants. Jupiter, the largest planet, is a swirling mass of clouds and storms, with its great red spot being a massive storm larger than Earth that has raged for centuries. Saturn is famous for its stunning rings made of ice and rock particles, which are the most elaborate in our solar system. Uranus is unique because it rotates on its side, giving it a distinct blue color from the methane in its atmosphere and leading to extreme seasonal changes. Lastly, Neptune, with its deep blue hue, is known for fierce winds and storms. It also has a moon, Triton, that has geysers ejecting nitrogen gas, hinting at intriguing activity beneath its icy surface. Each planet tells a story, showcasing a diverse range of environments, atmospheres, and features that make our solar system endlessly fascinating. The Moon has a profound impact on Earth, influencing various systems in ways that are essential to our planet's environment and ecosystems. One of the most significant effects is its role in creating tides. As the Moon orbits Earth, its gravitational pull creates bulges in the ocean, leading to the rise and fall of sea levels. These tidal movements are not just fascinating phenomena, they play a crucial role in coastal ecosystems. Tides help to distribute nutrients in the water, supporting the health of marine life and creating unique habitats like tidal pools where diverse species thrive. Moreover, the Moon stabilizes Earth's axial tilt. This stability is crucial for maintaining a consistent climate over long periods. Without the Moon's gravitational influence, our planet's tilt could vary more dramatically, leading to severe changes in climate that might make it difficult for many species, including humans, to adapt. This steadiness allows for predictable seasons, which are vital for the life cycles of plants and animals. Furthermore, the Moon affects nocturnal animals and their behaviors. Many species rely on the natural light provided by the Moon to navigate, hunt, and mate. The phases of the Moon can signal different activities, such as when certain fish spawn or when predators hunt in the cover of darkness. The gentle glow of moonlight impacts the rhythm of life, tying animals' behaviors to the lunar cycle. In addition to these direct effects, the moon's presence has also inspired cultures and impacted human activities since ancient times. Farmers rely on lunar cycles for planting and harvesting crops, and communities celebrate events timed with the full moon. Overall, the moon is not just a distant rock in the sky. Its gravitational pull shapes the oceans, stabilizes the climate, influences wildlife, and enriches human culture, making it an integral part of life on Earth. The asteroid belt is a vast region between the orbits of Mars and Jupiter, home to numerous rocky bodies known as asteroids. One key characteristic of these asteroids is their size variation, ranging from small pebbles to hundreds of kilometers across. Despite being numerous, most asteroids are relatively small, with the largest being quite significant, comparable to a dwarf planet. Another important feature is their composition. Asteroids can be made primarily of rock, metal, or a mixture of both. The type of material often provides clues about the early solar system, as many asteroids are considered leftover building blocks from its formation. Some asteroids contain metals like nickel and iron, while others have a clay-like or carbon-rich composition, indicating a variety of conditions in which they formed. The orbits of these celestial objects are also interesting. They typically follow stable, predictable paths around the Sun, with some having more eccentric shapes than others. This region is not densely packed. There is significant space between the asteroids. This makes the prospect of collisions relatively low, although they do occur from time to time. Additionally, many asteroids have unique characteristics, such as craters and surface features, that tell us about their history and exposure to forces like solar radiation. Some of them even possess their own moons, demonstrating that even smaller bodies in the solar system can have complex relationships. Understanding these key characteristics helps scientists piece together not only the history of the solar system, but also the potential resources that these asteroids might hold for future exploration. The asteroid belt is a fascinating window into the past, offering clues about the formation of planets and the materials available in our cosmic neighborhood. Comets are unique and intriguing members of our solar system, setting themselves apart from other celestial bodies, such as planets and asteroids. A comet can be best described as a dirty snowball. This means it consists mainly of ice, dust, and rocky materials. When a comet approaches the Sun, the heat causes the ice to vaporize, creating a glowing envelope called a coma and often forming a tail that extends away from the Sun. This tail is a stunning sight, highlighting one of the key differences. Unlike other objects, comets become vividly bright and visible when they near the Sun. In contrast, planets are large, spherical bodies that orbit the Sun and have cleared their paths of debris. Asteroids, on the other hand, are mostly rocky and metallic objects found primarily in the asteroid belt, lacking the icy components that define comets. The trajectory of comets is also distinct. They typically have elongated orbits that can take them far beyond the outer planets and deep into space, sometimes not returning to the inner solar system for many years or even centuries. Another fascinating aspect of comets is their origin. Most comets come from two main regions: the Kuiper belt, which lies beyond Neptune, and the Oort cloud, a distant sphere of icy bodies surrounding our solar system. These regions are like cosmic reservoirs of cometary material, explaining why comets are thought to be some of the oldest building blocks of our solar system. Comets stand out due to their icy composition, dramatic tails formed when near the Sun, unusual elongated orbits, and their origins in specific regions filled with primordial material. Together, these characteristics make them captivating objects of study for astronomers and space enthusiasts alike. Studying the surface conditions of Mars has revealed a wealth of information about our neighboring planet. First and foremost, scientists have discovered that Mars once had liquid water on its surface, indicated by features resembling riverbeds and lakebeds. This suggests that earlier in its history, Mars was much warmer and wetter than it is today, potentially making it suitable for life. The Martian atmosphere is incredibly thin, primarily composed of carbon dioxide, with only traces of oxygen and water vapor. This thin atmosphere cannot retain heat effectively, leading to dramatic temperature fluctuations, from relatively warm days to extremely cold nights. The presence of dust storms, which can envelop the planet for months, highlights how dynamic and harsh the environment can be. We've also learned about the planet's surface geology. Mars is home to the tallest volcano in the solar system, Olympus Mons, and vast canyon systems like Valles Marineris, which offer insights into volcanic and tectonic activity. These features tell us about the geological history and the forces that have shaped the landscape over billions of years. In addition to physical features, studying polar ice caps has provided clues regarding seasonal changes and climate patterns, showing cycles of freezing and thawing. These ice caps consist of water ice and carbon dioxide ice, revealing that even today, Mars may have some limited ability to store water. Overall, our exploration of Mars has reshaped our understanding of planetary evolution and the potential for life beyond Earth, while also fueling questions about the planet's future and the possibility of human exploration. The outer planets, often referred to as gas giants, differ significantly from the terrestrial planets, which are found closer to the Sun. While terrestrial planets, such as Earth, Mars, Venus, and Mercury, are composed primarily of solid rock and metals, the outer planets, Jupiter, Saturn, Uranus, and Neptune, are made up mainly of gases and liquids. The outer planets are much larger in size and have thick atmospheres dominated by hydrogen and helium. Imagine these planets as enormous balls of gas surrounding a smaller, possibly molten core. Their immense gravity allows them to hold on to these lighter gases, creating their distinctive features, like the swirling storms and bands seen on Jupiter. In contrast, terrestrial planets have a solid surface where we can walk and explore. Their materials are denser and include silicate rock and various metals. The solid surface is one reason we can easily land spacecraft on these planets, whereas landing on the gas giants would be impossible due to their lack of a defined surface. Moreover, the outer planets often have many moons, and some have ring systems made of dust and ice particles. This is quite different from the terrestrial planets, which have fewer moons and no prominent ring systems. So, while terrestrial planets are rocky with solid surfaces, the outer planets are vast, gas-filled worlds that offer a mesmerizing glimpse into a very different part of our solar system. Missions aimed at exploring Europa and other icy moons of Jupiter and Saturn have several exciting scientific objectives. Among the most important goals is the search for signs of life. Europa, in particular, is intriguing because it is believed to have a vast ocean of liquid water beneath its icy surface. Scientists think that this ocean may have the necessary conditions to support life, so understanding its composition and whether it has the right chemistry is vital. Another objective is to study the moon's surface and the ice that covers it. By analyzing the surface features and dynamics, scientists can gather clues about the ocean beneath, including its potential for habitability. Spacecraft may look for organic molecules, the building blocks of life, and analyze the geology to understand how these environments evolve over time. Understanding the interaction between the Moon and its parent planet's magnetic field is also crucial. This interaction could tell us about the ocean's thickness and the Moon's internal structure. Developing detailed maps of the surface will help scientists learn about the Moon's history and any tectonic or geological activity, revealing how the Moon has changed over time. Additionally, the presence of plumes, water vapor, and other materials ejected from the surface offers another opportunity for study. If missions can capture samples from these plumes, they may provide direct evidence of the ocean below and what it contains, enhancing our understanding of possible extraterrestrial environments. Overall, these missions not only aim to answer questions about Europa and similar moons, but also influence our broader understanding of the potential for life in our solar system and beyond. Each objective helps unravel the mysteries of these fascinating worlds, contributing to the emphasis on exploring our cosmic neighborhood. Recent discoveries in astronomy have reshaped our understanding of the universe in profound ways. One of the most exciting advancements has been the detection of gravitational waves. These ripples in space-time, produced by massive events like the collision of black holes or neutron stars, provide a new way of observing the cosmos, allowing scientists to hear what was once silent. This discovery confirmed a prediction made by Albert Einstein over a century ago, opening up a new field of astrophysics. Another groundbreaking achievement is the capture of an image of a black hole's event horizon. Using a network of telescopes around the globe, astronomers succeeded in visualizing the shadow of a black hole in a distant galaxy. This moment marked a pivotal step in understanding these mysterious objects and backed the theory of their existence. The discovery of exoplanets, particularly those situated in the habitable zones of their stars, has also transformed our perspective. Thousands of such planets have been identified, some strikingly similar to Earth. This raises intriguing possibilities about life beyond our planet and the potential for other civilizations in the cosmos. Moreover, studies of dark energy, the mysterious force driving the accelerated expansion of the universe, continue to challenge existing theories. New observations have helped refine our understanding, yet dark energy remains one of the greatest puzzles in modern science, prompting questions about the fate of the universe itself. Finally, the ongoing exploration of Mars and the discovery of signs of ancient water further enrich our quest to understand the potential for life elsewhere. By examining the red planet's history, scientists hope to learn whether conditions existed there that could have supported life, connecting us to the broader narrative of our solar system. These advancements and more are not just scientific milestones. They ignite the imagination and push us to explore our place in the universe, urging us to seek answers to the fundamental questions about existence, life, and the cosmos. The detection of gravitational waves provided a profound confirmation of Einstein's theory of relativity, specifically his concept of gravity as a curvature of space and time. Think of space and time as a flexible fabric that can bend. When massive objects like black holes or neutron stars collide, they create ripples or waves in this fabric. These ripples travel outward at the speed of light, carrying information about such powerful cosmic events. Before the first detection of these gravitational waves in 2015, scientists had only predicted their existence based on mathematical calculations. The moment they were observed, it was like observing the very vibrations of space-time itself, validating Einstein's idea that gravity is not just a force, but a dynamic interplay of geometry. The waves that were detected came from two black holes spiraling in toward each other, ultimately merging. This collision created a distortion in space and time that stretched and compressed everything in its path. When researchers analyzed the data, they found that the characteristics of the gravitational waves matched precisely with predictions made by relativity. This was not merely an affirmation of theory, it opened up a new way to observe the universe. With this detection, scientists gained an innovative tool for studying cosmic phenomena. They could now listen to the universe in a different way, piecing together the history of events that occurred far beyond what optical telescopes can see. The confirmation of gravitational waves showed that Einstein's framework of relativity holds true in the most extreme conditions imaginable, reshaping our understanding of the cosmos and how its fundamental forces interact. The discovery of water on Mars is a groundbreaking finding that opens up exciting possibilities for future exploration. Water is essential for life as we know it, and finding it on another planet raises hopes that life may have existed there or might exist in some form. This revelation shifts Mars from being seen solely as a barren landscape to a place with potential resources for human missions. In practical terms, water can be used to support future astronauts traveling to Mars. It can provide drinking water, be converted into breathable oxygen, and serve as a component in producing rocket fuel for return journeys to Earth or travel deeper into space. This means that future missions could potentially be less dependent on transporting all supplies from Earth, making long-duration exploration more sustainable. Furthermore, the presence of water suggests that Mars has a dynamic history. Scientists can study the past environment of the planet by examining ice deposits and searching for minerals associated with water. Understanding these aspects can help answer fundamental questions about the planet's geology and climate, informing our strategies for exploration. Finding water on Mars signifies a pivotal moment for future exploration, as it enhances the possibilities for human settlement, provides critical resources, and deepens our understanding of the planet's history and potential for life. This knowledge not only shapes mission planning, but also inspires humanity's enduring quest to explore the cosmos. Recent breakthroughs in quantum physics have profoundly changed how we understand the universe. At its core, quantum physics studies the smallest particles that make up everything around us. These particles behave in ways that are often puzzling, with phenomena that challenge our traditional views of reality. For instance, one important discovery is the concept of entanglement, where two particles can be connected in such a way that the state of one instantly influences the other, no matter how far apart they are. This idea has led scientists to rethink the connections between distant objects in the universe, suggesting a level of interrelationship that we previously did not consider. Additionally, quantum physics has contributed to our understanding of black holes and the events that occur at their centers. Theories emerge that the mysteries surrounding black holes involve both quantum mechanics and general relativity, which describes gravity. This merging hints at a deeper, more intricate framework of the cosmos, where the smallest scales of nature intertwine with the vastness of space. Moreover, quantum approaches have opened up new avenues in the field of cosmology, allowing for models of the early universe that explain how it expanded after the Big Bang. These models incorporate quantum effects at the moment of creation, providing insights into how the universe evolved and creating the conditions we observe today. Overall, breakthroughs in quantum physics not only deepen our understanding of matter and energy, but also reshape our view of the universe, suggesting that everything is interconnected in ways that transcend our ordinary perceptions. Each new discovery offers a piece of a larger puzzle, encouraging us to keep exploring the fundamental nature of reality itself. Recent discoveries in astronomy have profoundly altered our understanding of the universe's scale. One of the most significant shifts has come from advancements in the study of exoplanets, those planets located outside our solar system. With powerful telescopes and improved detection methods, scientists have identified thousands of these distant worlds, suggesting that planetary systems are common throughout the cosmos. This realization expands our notion of the universe, making it seem much more populated than previously thought. Another watershed moment came from the precise measurements of the universe's expansion rate, known as the Hubble constant. New data from various telescopes have revealed discrepancies in this rate when observed from different distances. This inconsistency hints at complexities in our understanding of dark energy, the mysterious force that drives the universe's expansion. Scientists are considering new models of the cosmos to explain why different methods yield different results, suggesting that our current grasp on cosmic expansion may be incomplete. Additionally, the detection of gravitational waves has opened a new window into the universe. These ripples in space-time, caused by cosmic events like merging black holes, provide a fresh way to observe occurrences beyond traditional light-based telescopes. Gravitational waves allow us to probe phenomena that were once invisible, significantly broadening our view and understanding of the universe's scale and the events that shape it. Lastly, the imaging of the black hole at the center of a massive galaxy marked a monumental milestone. It was the first direct visual confirmation of a black hole's existence, demonstrating not only how massive these objects can be, but also reinforcing theories about how galaxies evolve around them. This single image brought clarity to the chaotic dance of matter and energy that defines the structure of our universe. Together, these discoveries challenge our previous models and push the boundaries of what we know about the universe, urging us to think of a cosmos that is richer and more dynamic than we ever imagined. New imaging technologies have revolutionized astronomical research, providing clearer and more detailed views of the universe than ever before. In the past, astronomers often worked with telescopes that had limitations, capturing only faint and fuzzy images of distant stars and galaxies. Today, advanced imaging techniques allow scientists to photograph the cosmos with remarkable precision. One of the significant advancements is the use of adaptive optics. This technology helps to correct distortions caused by Earth's atmosphere, similar to using a pair of glasses to sharpen blurry vision. As a result, astronomers can observe celestial bodies with nearly the same clarity as if they were in space. This improved clarity allows for detailed studies of star formation, planet atmospheres, and even the dynamics of galaxies. Another key development is the use of infrared and radio imaging. These methods let scientists see objects that are not visible in regular light, such as the heart of dusty regions where stars are born or the cool remnants of dead stars. By capturing a broader range of wavelengths, astronomers can piece together a more complete picture of celestial phenomena, unveiling hidden aspects of the universe. Additionally, modern space telescopes like the Hubble Space Telescope have further enhanced our capabilities. Orbiting above Earth's atmosphere, these telescopes observe the universe without interference, leading to stunning images that unveil ancient galaxies and distant exoplanets. These space-based observations provide invaluable data for understanding cosmic evolution and the conditions that lead to the formation of life. With the rise of digital technology, capturing and analyzing vast amounts of data has become more efficient. Automated processes allow researchers to sift through astronomical images rapidly, helping to identify new celestial objects and phenomena. This data-rich approach permits more extensive surveys of the sky, enabling discoveries that reshape our understanding of the universe. Advancements in imaging technologies have made astronomical research more precise and expansive, providing insights into phenomena that were once beyond our reach. Each new technique opens the door to new discoveries, allowing humanity to explore the cosmos in unprecedented ways. The field of astronomy is on the brink of remarkable advancements that could reshape our understanding of the universe. One of the most exciting developments is the ongoing progress in telescope technology. Scientists are building highly sophisticated telescopes that can detect faint light from distant stars and galaxies, even those billions of light-years away. These instruments have the potential to unveil cosmic phenomena that have remained hidden from our eyes, giving us deeper insights into the origins of the universe. Another significant area of focus is the search for extraterrestrial life. Missions to various planets and moons in our solar system aim to uncover signs of life or conditions that might support life. For instance, the exploration of icy moons like Europa, which likely harbors a subsurface ocean, could reveal if life exists beyond Earth. This search is not limited to our neighboring planets. Astronomers are also using powerful instruments to look for biosignatures or signs of life in the atmospheres of distant exoplanets. Additionally, advancements in the understanding of dark matter and dark energy are poised to transform our grasp of the cosmos. Although these components make up much of the universe, they remain elusive. Researchers are developing new experiments to detect dark matter particles and to understand the accelerating expansion of the universe driven by dark energy. Gaining clarity on these mysteries could reshape foundational theories of physics. Moreover, the coming decade promises to be monumental for gravitational wave astronomy. New observatories will enhance our ability to detect ripples in space-time caused by massive astronomical events like the merging of black holes. This development allows us to explore the universe in ways that were previously unimaginable, providing a complementary approach to traditional observational methods. Combined, these advancements in technology, exploration, and theoretical research indicate a vibrant future for astronomy. We stand at the edge of discovery, eager to explore the universe's vastness and unlock its secrets, potentially answering some of humanity's oldest questions about our place in the cosmos. As we peer into the distant future of our universe, we enter a realm of intriguing possibilities shaped by cosmic evolution. Picture the universe stretching out over vast expanses, galaxies drifting farther apart as time passes. This phenomenon begins to create a cosmic landscape where the night sky, once teeming with countless stars, transforms into a more empty and desolate view. One scenario foresees a time when many stars will have burned out, leaving behind only remnants like white dwarfs and neutron stars. Eventually, even these stellar remnants will grow cold and dim, resulting in a universe dominated by black holes and faint, inactive matter. With fewer active stars, the vibrant glow of galaxies will fade into the darkness. For those who consider time on the grandest scale, the concept of cosmic dark ages arises. This is a period when new star formation has ceased, and the universe will enter a stage characterized by an eerie silence where light from stars has mostly vanished. The universe will become a vast, dark expanse filled with the frozen remnants of once vibrant celestial bodies. Meanwhile, black holes might continue to quietly consume everything around them. Over immense periods, they could merge and grow larger, forming supermassive black holes. These entities could be the cosmic giants of a future universe that appears utterly still and dominated by gravity. Additionally, there's a thought-provoking idea called the heat death of the universe. In this scenario, all energy would balance out evenly, and no usable energy would remain. The universe would reach a state of maximum entropy, essentially a state of ultimate disorder where every element is evenly spread out and nothing happens. In this distant future, the cosmos may seem lifeless, yet it is a testament to the dynamic history it once held. An expanse where galaxies roamed freely, stars ignited and extinguished, and life flourished will evolve into a calm and slow fading of cosmic history, stripped of its once thrilling tales. Ultimately, contemplating the future of our universe inspires wonder about our existence within this vast and ever-changing cosmos. When we look at time on a cosmic scale, it changes in ways that are quite surprising compared to our everyday experiences. On Earth, a second feels like a fixed unit, a brief moment that we can measure easily. However, in the vastness of space, time is much more relative, influenced by gravity and speed. Imagine watching a distant star. The light from that star takes years, sometimes millions or even billions of years, to reach our eyes. This means that what we observe is not the star as it is today, but rather how it looked long ago. In a sense, when we gaze at the night sky, we are looking back in time. Additionally, near massive objects like black holes, time behaves differently. The intense gravity around these objects stretches time, so that for someone far away, it appears to pass slowly for someone close to the black hole. This phenomenon is called gravitational time dilation. It's as if the flow of time can speed up or slow down, depending on where you are in the universe. This interplay of gravity and motion creates a complex tapestry of time throughout the cosmos, where two observers can experience time in completely different ways based on their relative positions and movements. The cosmos reveals to us that time is not simply a universal constant, but a fluid concept that dances in accordance with the forces of the universe. The ultimate fate of the universe is a subject of deep curiosity and complex scientific theories. One widely discussed possibility is known as the Big Freeze. As the universe expands, it continues to get colder. In this scenario, galaxies drift further apart until they are isolated in a vast, dark, and empty space. Eventually, stars will burn out, leaving behind only black holes and faint remnants of matter. This continuous expansion leads to an ever cooler universe, ultimately leading to a lifeless, frozen end. Another intriguing theory is the Big Crunch. This idea proposes that the expansion of the universe might eventually slow down and reverse due to gravitational forces. In this situation, everything would start to come back together, leading to a collapse of the universe back into an extremely hot and dense state. This could theoretically lead to a scenario similar to the one that began the universe, possibly setting the stage for another Big Bang and the cycle of creation starting anew. A different possibility is the concept of Big Rip. In this theory, the universe continues to expand at an accelerating rate, driven by a mysterious force called dark energy. Gradually, this acceleration could tear apart galaxies, stars, and even atomic particles. In this scenario, everything would be ripped apart entirely until only scattered particles remain, swiftly moving away from each other. There are also unique theories like heat death, where the universe reaches a state of maximum entropy. In simpler terms, this means a point where energy is evenly distributed and no more work can be done. All processes cease, resulting in a still, uniform universe with no structure. Each of these theories presents a different vision for the future of our universe, sparking the imagination while also raising profound questions about existence, time, and the nature of everything we know. As scientists continue to study cosmic phenomena, our understanding of the final fate of the universe may evolve, keeping the mystery alive for generations to come. The concept of time is deeply woven into the fabric of our understanding of the universe. Initially, time was seen as simple and linear, much like a straight line stretching from past to future. Ancient philosophers and early scientists viewed it as something fixed, a constant flow that ticks steadily away regardless of events. However, as scientific inquiry progressed, so did our perceptions of this elusive dimension. With the advent of modern physics, particularly in the early 20th century, our understanding began to shift dramatically. Albert Einstein's theory of relativity introduced a groundbreaking idea. Time is not an isolated entity, but closely linked with space, forming what we now call spacetime. This theory posits that the passage of time can vary based on speed and gravity. For instance, an observer moving at a significant fraction of the speed of light would experience time differently than someone who remains still. This revelation fundamentally changed how scientists think about time, suggesting it is flexible rather than rigid. As research continued, concepts such as the expansion of the universe presented even more complexity. Time seemed to expand along with space, creating a rich interplay between these two dimensions. Further exploration into black holes revealed that immense gravitational forces could stretch and warp time to the point where it behaves in ways that defy everyday experience. Near a black hole, time can slow down drastically compared to distant observers, highlighting the intricate relationship between gravity and time. Today, physicists continue to explore the nature of time, especially in the context of quantum mechanics, which describes the behavior of the smallest particles. Here, time can seem less predictable, as particles may not have a defined state until observed. This leads to fascinating questions about the flow of time and whether it even exists as we perceive it at the quantum level. The evolution of our understanding of time reflects a journey of discovery, where each new theory has built upon the last, weaving a complex narrative that challenges our most basic intuitions. As we continue to probe deeper into the mysteries of the universe, who knows how our perception of time may transform yet again? The fate of our solar system is tied to the life cycle of our sun, a star that will eventually exhaust its fuel. Currently, the sun is in its middle years, steadily converting hydrogen into helium through a process called nuclear fusion. This stage has lasted for billions of years and will continue for several more billion years. However, as the sun consumes its hydrogen, it will undergo significant changes. In the distant future, as it runs low on hydrogen, the core of the sun will contract under gravity, while the outer layers will begin to expand. This transformation will turn the sun into a red giant. During this phase, it will engulf the inner planets, including Mercury and likely Venus, and possibly even Earth. This dramatic expansion will lead to intense heat and radiation, effectively sterilizing any life that might exist near the sun. Eventually, the sun will shed its outer layers, creating a colorful shell of gas and dust known as a planetary nebula. The core that remains will shrink down to form a white dwarf, an extremely dense object that will gradually cool over the span of billions of years. This white dwarf will no longer have the energy to shine brightly, but will eventually fade into a cold, dark state known as a black dwarf, a theoretical end state that would take longer than the current age of the universe to reach. As the Sun evolves, the gravitational influence it exerts will also diminish, affecting the orbits of the outer planets. They may drift farther into space, and their dynamics will alter as the solar system undergoes these changes. While this may sound startling, these events are not imminent. They are part of a natural cosmic cycle. The end of our solar system, in the form of the Sun's demise, is a story written in the stars, unfolding over an immense timescale far beyond our human experience. Time travel captivates both scientists and dreamers alike, simultaneously rooted in modern physics and running wild in our imaginations. The concept begins with the understanding that time is not as fixed as we might think. Instead, it is intertwined with space itself, forming a four-dimensional fabric known as spacetime. This connection suggests that moving through space can affect how we experience time. One foundational theory that introduces the idea of time travel is Einstein's theory of relativity. In this framework, the faster you travel through space, the more slowly you experience time compared to someone stationary. Imagine two twins. One stays on Earth while the other flies in a spacecraft at incredible speeds. When the traveling twin returns, they will be younger than the one who remained on the planet, illustrating how high speed can lead to a different flow of time. But there are even bolder ideas. The existence of theoretical constructs like wormholes might provide a means to shortcut through spacetime, potentially allowing travel between distant points or even back in time. A wormhole can be visualized like a tunnel connecting two separate locations in the universe. If these tunnels exist and could be stabilized, they might grant a passage not just through space, but also through the temporal dimensions. However, time travel is not without complications. Theories involving time travel often raise paradoxes, such as the famous grandfather paradox, where a time traveler could fundamentally alter the past. Questions like these challenge our understanding of causality and the very nature of time. Current scientific exploration still deals with many mysteries, and while the notion of time travel sparks thrilling possibilities, it rests on speculative foundations. For now, these concepts prompt us to ponder the nature of time itself, showing that while time travel may not yet fit neatly in our grasp, it remains a fascinating topic at the intersection of physics and imagination. As humanity looks to the stars, emerging technologies have the potential to revolutionize our understanding of time in space exploration. A pivotal focus is on the concept of propulsion systems that could significantly reduce travel times. For instance, advanced ion propulsion and solar sails could propel spacecraft much faster than current chemical rockets, making journeys to distant planets and moons more feasible. With shorter travel times, the experience of time for astronauts might feel different compared to time on Earth, creating fascinating scenarios for how time could be perceived in space. Another exciting development lies in the realm of relativity and time dilation, which occurs near massive celestial bodies or at near-light speeds. Future technologies may allow us to navigate scenarios where time behaves differently. By using faster-than-light propulsion theories, like warp drives, we could move through space in a way that compresses time experienced by travelers compared to those remaining on Earth. This would lead to intriguing possibilities where astronauts could return from distant missions having aged less than their friends and family back home. Additionally, advancements in artificial intelligence are set to enhance our ability to manage time during long-duration missions. AI could optimize schedules, ensuring that astronauts maintain their physical and mental health, thus altering their perception of time. With efficient planning, the journey might feel shorter and the days could become more structured, blending work and leisure seamlessly. Moreover, virtual reality could play a role in time perception. During long trips, VR environments might engage astronauts and manage their psychological well-being, creating immersive experiences that help distort their sense of time. Hours could pass unnoticed as they explore virtual worlds while simultaneously traveling vast distances in space. As these technologies develop, they promise to reshape our relationship with time, not just by minimizing its passage, but also by changing how we experience it entirely. Each leap in technology not only pushes the boundaries of our physical journey through space, but also invites us to reflect on the very nature of time itself. Space telescopes have transformed our understanding of distant galaxies by providing a clear, unobstructed view of the universe. Unlike ground-based telescopes, which must overcome Earth's atmosphere, space telescopes sit above it, avoiding the blurring and distortion that can affect observations. This clearer perspective allows scientists to see finer details and capture light from objects that are incredibly far away. These telescopes are equipped with advanced instruments that can detect different types of light, not just visible light. Some can observe infrared light, which is often emitted by cool, distant objects like star-forming regions or newly formed stars hidden within dust clouds. Others might focus on ultraviolet light, which helps identify the hottest and youngest stars in a galaxy. By studying a wide range of wavelengths, space telescopes can build a more complete picture of what galaxies look like and how they evolve over time. Moreover, these celestial instruments allow scientists to look back in time. Due to the finite speed of light, when we observe distant galaxies, we are actually seeing them as they were millions or even billions of years ago. This ability to survey the universe at different moments in time helps researchers understand how galaxies form, mature, and interact with one another. It opens a window to witness cosmic events like the birth of stars and the merging of galaxies. Additionally, space telescopes enable the study of exoplanets orbiting distant stars. By analyzing how starlight dims as a planet passes in front of its star, scientists can infer information about the planet's size and atmosphere. This insight is crucial in the ongoing quest to find Earth-like worlds and understand their conditions. Space telescopes offer a vital glimpse into the cosmos, enhancing our knowledge of distant galaxies with unparalleled clarity and depth. With every observation, they unveil new secrets about the structure of our universe, painting a clearer picture of its past, present, and future. To observe cosmic phenomena, scientists utilize a range of innovative methodologies that enhance our understanding of the universe. One of the foundational techniques is the use of telescopes, but they are not just ordinary devices. Astronomers have developed various types that work across different parts of the electromagnetic spectrum. For instance, optical telescopes capture visible light, while radio telescopes detect radio waves emitted by distant galaxies, providing insights into their structure and behavior. Another exciting method involves the use of space-based observatories. By placing instruments above Earth's atmosphere, scientists can avoid interference caused by atmospheric conditions. This allows for clearer and more detailed observations of celestial objects. Space telescopes, like the Hubble Space Telescope, have provided breathtaking images and critical data, revealing the intricate details of galaxies, nebulae, and other cosmic structures. In addition to traditional methods, astronomers employ advanced techniques such as spectroscopy. This process analyzes the light emitted or absorbed by objects in space to determine their composition, temperature, density, and velocity. By spreading light into its component colors, researchers can identify specific signatures that reveal the elements present in distant stars or the movement of galaxies. Gravitational wave detection is another frontier in cosmic observation. This methodology takes advantage of ripples in spacetime caused by massive events, such as the merging of black holes or neutron stars. Facilities like LIGO and Virgo use incredibly sensitive instruments to detect these minuscule changes, providing a completely new way of observing the universe and confirming key aspects of Einstein's theory of relativity. Moreover, computer simulations and artificial intelligence are becoming increasingly vital in interpreting vast amounts of data collected from various observations. These technologies can help identify patterns and anomalies in cosmic phenomena that might not be visible to the human eye or deduced through conventional analysis. As technology continues to evolve, so too will our methods for observing the cosmos, allowing us to unlock even deeper mysteries of the universe. Each innovative approach brings us closer to answers about the origins of galaxies, the life cycles of stars, and the very nature of space and time itself. Radio telescopes and optical telescopes serve different purposes and operate in distinct ways, leading to unique capabilities in observing our universe. To understand the difference, picture these telescopes as specialized tools designed to capture different types of signals from space. Optical telescopes are designed to gather light that is visible to our eyes. They use lenses or mirrors to focus this light, allowing us to observe celestial objects like stars, planets, and galaxies in great detail. These telescopes work best on clear nights when the sky is dark, as light pollution and atmospheric conditions can hinder their performance. Optical telescopes capture the beauty and color of the universe, revealing the intricate details of visible objects. In contrast, radio telescopes detect radio waves, which are a type of electromagnetic radiation with much longer wavelengths than visible light. Imagine tuning into a radio station. Radio telescopes pick up these cosmic signals from space. They consist of large dish-like structures that collect and focus radio waves onto a receiver. This allows scientists to study phenomena that optical telescopes often cannot detect, such as the cold gas clouds in space or the faint emissions from distant galaxies. One key advantage of radio telescopes is their ability to see through dust and gas that obstruct light in the optical spectrum. This means they can observe objects that are hidden from view, providing insights into the formation of stars and the dynamics of galaxies. Additionally, radio observations can be made during the day or night, making these instruments versatile in their operational time. Both types of telescopes are essential for a comprehensive understanding of the universe, each revealing different aspects of celestial phenomena. Together, they create a richer picture of space, showing us not just what we can see with our eyes, but also the hidden dynamics at play in the cosmos. Adaptive optics has revolutionized modern astronomy by allowing us to see the universe with astonishing clarity. At its core, adaptive optics corrects the blurring caused by the Earth's atmosphere. Imagine looking at a distant star through a thick fog. It's challenging to make out details. Adaptive optics acts like a pair of glasses for telescopes, sharpening the image and enabling astronomers to study celestial bodies more accurately. One key application of this technology is in ground-based telescopes. Traditional telescopes face challenges due to fluctuations in atmospheric conditions, which can distort light from objects in space. With adaptive optics, telescopes can adjust in real time to these distortions. A system within the telescope monitors the incoming light and uses a flexible mirror to change its shape, counteracting the blurriness and providing a sharper view of stars and galaxies. This allows for more precise measurements of brightness and size. Another significant application lies in the observation of exoplanets. These planets orbit stars far away and are extremely faint compared to their luminous neighbors. Adaptive optics enhances the ability to detect these distant worlds by minimizing the effects of turbulence in the atmosphere, making it easier to spot the faint glow of a planet next to a bright star. Furthermore, adaptive optics has greatly contributed to our understanding of the dynamics of galaxies. By observing details like star formation and the movements of stars within galaxies, scientists can learn how galaxies evolve over time. This technology also aids in the study of cosmic phenomena such as supernovae and black holes, allowing researchers to capture more detailed images and gather essential data. Additionally, adaptive optics plays a vital role in the field of spectroscopy, where it allows scientists to analyze the composition of distant objects by examining the light they emit or absorb. By obtaining clearer spectral data, astronomers can infer details about the chemical makeup and physical properties of celestial bodies. Adaptive optics enhances the power of telescopes, enabling clearer images of distant objects, improving our ability to detect faint exoplanets, revealing the intricate details of galaxies and providing critical insights into the universe's composition. This technology is central to advancing our understanding of the cosmos. Spectrometry is a powerful tool used to analyze the light coming from stars and other celestial bodies. When starlight is captured through a telescope, it often passes through a device called a spectrometer. This device splits the light into its constituent colors, creating a spectrum much like a rainbow. By examining this spectrum, scientists can gather essential information about what the star is made of. Each element in the universe emits and absorbs light at specific wavelengths, which are like unique fingerprints. For example, hydrogen and helium produce distinct lines in a spectrum. These lines appear as dark or bright bands spread across the spectrum, indicating the presence of certain elements. When scientists spot these patterns, they can identify which elements are present in a star. Moreover, the intensity of these spectral lines provides insights into the abundance of each element. A brighter line suggests more of that element is present, while a fainter line indicates less. Additionally, the shape of these lines can reveal information about the temperature, pressure, and motion of the star. If a star is moving towards us, its spectral lines are compressed, shifting towards the blue end of the spectrum. Conversely, if it is moving away, these lines shift towards the red end. Through spectrometry, not only can we determine what stars are made of, but we can also learn about their physical properties and behaviors, enabling a deeper understanding of the universe itself. This technique has thus become a cornerstone in the field of astrophysics, allowing us to uncover the mysteries of the cosmos from light that travels for millions of years to reach us. Satellites serve as our vigilant observers in the vast expanse of space, playing an essential role in monitoring cosmic activity. They are equipped with advanced instruments that can capture a wide spectrum of data about celestial phenomena. By orbiting the Earth or traveling much further into space, these satellites provide continuous coverage and can detect events like solar flares, asteroid movements, and cosmic radiation. One of the primary jobs of satellites is to watch our sun. Solar activity, such as flares and coronal mass ejections, can have significant effects on Earth, including disruptions to communication systems and power grids. Satellites like those in a fleet dedicated to solar observation are equipped with specialized sensors that can measure magnetic fields and solar particles, allowing scientists to predict when these events might occur. Moreover, satellites are critical in tracking near-Earth objects, like asteroids, that could pose a threat to our planet. By identifying their paths and tracking their movements, scientists can assess the potential risk of impact and develop strategies to mitigate it if necessary. In addition to monitoring objects closer to home, satellites also observe distant cosmic events. They collect valuable information about supernovae, the birth of stars, and the interactions of galaxies. By studying cosmic microwave background radiation, satellites help us understand the early universe and the origins of cosmic structures. Satellites act as our eyes in the sky, providing invaluable data that enriches our understanding of the universe and helps protect our home planet from cosmic threats. Their ability to gather and relay information in real time is crucial for both scientific research and for maintaining the safety of our technological systems on Earth. Innovations in spectroscopy have dramatically transformed our understanding of space by allowing scientists to analyze the light emitted or absorbed by objects in the universe. At its core, spectroscopy studies how light interacts with matter. When light passes through a material, it can give us a unique fingerprint of that material, revealing its composition, temperature, density, and even motion. Imagine looking at a rainbow. Each color corresponds to different wavelengths of light. When astronomers analyze the light from stars, galaxies, or even planets, they can separate it into its individual colors, much like a rainbow. This process reveals specific dark lines, known as absorption lines, and bright lines, known as emission lines. These lines indicate the presence of certain elements and compounds, such as hydrogen, helium, and carbon. By examining these lines, scientists can determine what materials are present in distant celestial bodies. Furthermore, advancements in technology have improved the sensitivity and precision of spectroscopic instruments. This means we can now detect light from much fainter objects and at greater distances than ever before. For example, the Hubble Space Telescope has provided incredible spectral data that has led to significant discoveries, like the presence of water vapor in exoplanets and the detection of complex organic molecules in distant galaxies. This technique has also unveiled essential information about the universe's expansion. By measuring the spectral shift of light from galaxies, scientists can determine how fast they are moving away from us. This discovery laid the groundwork for understanding dark energy, the mysterious force driving the acceleration of the universe's expansion. Innovations in spectroscopy not only deepen our knowledge of what substances compose our universe, but also help us explore fundamental questions about its structure and evolution. This vibrant field continues to enhance our view of the cosmos piece by piece, painting a clearer picture of the vastness that surrounds us. The concept of faster-than-light travel captivates scientists and dreamers alike. They explore various theoretical ideas, even though current laws of physics suggest it is impossible. One of the most popular concepts is the idea of warp drives. Imagine stretching space behind a spacecraft while compressing space in front. This creates a bubble that allows the ship to move faster than light without actually breaking any physical laws. Inside this bubble, the ship remains stationary in its immediate surroundings as it rides the wave of distorted space. Another intriguing proposition is the existence of wormholes, which we mentioned earlier. These hypothetical tunnels could connect two distant points in spacetime. If someone were able to navigate through a wormhole, they could potentially travel vast distances in a very short time. However, the stability of such structures is still purely theoretical and requires exotic forms of matter that have not been discovered. Quantum mechanics introduces additional fascinating ideas, such as quantum tunneling, which suggests that under certain conditions, particles can cross barriers instantaneously. While this doesn't apply directly to larger objects or people, it shows that the universe is full of unexpected behaviors that challenge our understanding. Finally, it is essential to recognize that these theoretical possibilities often come with significant challenges. We have yet to find evidence of the necessary technology or principles to make these ideas a reality. Nevertheless, exploring the potential of faster-than-light travel offers a glimpse into the wonders of our universe and sparks the imagination about what the future may hold in our quest for the stars. Wormholes capture the imagination of both scientists and science fiction writers because they represent the possibility of shortcuts through space and time. For scientists, a wormhole offers a theoretical way to connect two distant points in the universe, drastically reducing the immense distances between them. This concept stems from the laws of physics, particularly the theory of general relativity, which allows for the bending of space. If such connections exist, they could enable travel to faraway stars and galaxies in ways we cannot yet achieve. Science fiction writers, on the other hand, embrace wormholes as a gateway to incredible storytelling. They envision characters leaping through these cosmic tunnels, embarking on adventures across galaxies in the blink of an eye. This opens up endless possibilities for exploring different worlds, meeting extraterrestrial civilizations, and confronting the unknown. Writers can play with the idea of time travel, where journeys through wormholes not only traverse space, but also allow characters to visit different periods in time. The blend of scientific theory and imaginative narratives makes wormholes a fascinating topic. They challenge our understanding of the universe while also igniting the creativity of writers. Whether as a potential reality or a plot device, wormholes stimulate curiosity about what lies beyond our current knowledge and inspire dreams of what the future might hold. This combination of rigorous science with fanciful storytelling creates a unique dynamic that continues to capture hearts and minds. Teleportation might sound like the stuff of science fiction, but at its core, it is grounded in fascinating principles of quantum physics. Imagine everything in the universe as being made up of tiny particles that follow specific rules. One of the key ideas in quantum physics is that these particles can exist in multiple states at the same time, a concept known as superposition. This means that before you observe them, a particle can be in several places or have various properties simultaneously. The concept of teleportation arises when we talk about transferring information about the state of a particle from one location to another without moving the particle itself. This transfer relies on another principle called quantum entanglement. When two particles are entangled, changes to one particle will instantaneously affect the other, no matter the distance separating them. Imagine having two identical magic coins. If you flip one and it lands on heads, the other coin will show heads too, no matter how far away it is. In a simplistic sense, achieving teleportation would involve scanning the state of a particle at its original location, sending that information to a distant place, and then recreating that state using a corresponding particle at the new location. This process does not transport matter in the traditional sense. Instead, it focuses on transmitting information about the arrangement and state of particles. While scientists have achieved successful teleportation of small particles, like atoms and photons, the leap to teleporting something as complex as a human being is currently beyond our reach. The challenges include the enormous amount of information involved, the need for perfect conditions, and the question of what it means to be you if your information were transported. Teleportation remains a thrilling concept, hinting at the mysterious and interconnected nature of particles in our universe. Interstellar travel captivates our imagination and fuels humanity's aspirations for the future. This notion offers a tantalizing possibility of journeying beyond our solar system to explore new worlds and unravel the mysteries of the universe. As we contemplate the vastness of space, interstellar travel serves as a symbol of our relentless pursuit of knowledge and adventure. The dreams of reaching distant stars inspire advancements in technology and science. Scientists and engineers envision spacecraft capable of incredible speeds, harnessing energy in ways we can only begin to imagine. The challenges of such journeys, like vast distances, extended life support systems, and the effects of time, push innovation forward, creating technology that can benefit life on Earth as well. Moreover, interstellar travel raises profound questions about our place in the cosmos. It prompts us to consider what lies beyond our horizon, igniting curiosity about the potential for extraterrestrial life and the future of humanity. The prospect of finding new homes for future generations expands our thinking about survival and sustainability. In a practical sense, the pursuit of interstellar travel could lead to international collaborations. Nations might unite in the spirit of exploration, pooling resources, knowledge, and expertise to achieve a common goal. This shared quest could strengthen bonds between cultures, promoting peace as we collectively reach for the stars. Ultimately, the concept of interstellar travel shapes our aspirations by encouraging us to dream bigger, think creatively, and work together. It reminds us of the boundless possibilities that lie ahead, urging us to reach beyond our limitations and explore the unknown. As we gaze into the night sky, the stars become not just points of light, but destination markers on a journey that could redefine humanity's future. Generation ships are a fascinating concept for exploring the universe and potentially establishing human colonies on distant planets. These massive vessels would be designed to carry people on long journeys that span multiple generations, allowing those on board to live their entire lives without ever reaching their destination, which could take many years or even centuries to arrive at. One of the key challenges of generation ships is the need to sustain life over extended periods. This includes providing a stable food supply, fresh water, and air. To achieve this, the ship would require advanced systems for recycling water and air, as well as large agricultural spaces or hydroponic systems to grow food. Moreover, the ship must be equipped with reliable energy sources, possibly using solar panels or other renewable methods to power these systems and support life. Another significant challenge is social dynamics. Life aboard a generation ship could become a complex social experiment, where generations of people must collaborate in a confined space. Issues such as governance, conflict resolution, and the handling of resources would need to be carefully managed to prevent tensions within the community. As no one on board would have first-hand experience of the outside universe, cultural and educational development would also be crucial for maintaining a balanced society during the long journey. Despite these challenges, the possibilities of generation ships are quite exciting. They could pave the way for human expansion into new realms, unlocking opportunities for colonization of planets that are currently beyond our reach. A successful generation ship could serve as a self-sufficient ecosystem, allowing humans to adapt and thrive in entirely alien environments. It represents a chance to study how humans might evolve socially and physically in different atmospheric and gravitational conditions over generations. Additionally, generation ships could be equipped with advanced technology for scientific research and exploration, giving their inhabitants the chance to document their findings and experiences. In a way, these ships may even serve as a microcosm of humanity, preserving cultural heritage and knowledge for future generations who would one day step onto a new world. Ultimately, while generation ships would face formidable hurdles, they represent an ambitious and innovative way to envision humanity's future among the stars, transforming the dream of space colonization into a tangible endeavor. Virtual reality technology has the potential to play a significant role in preparing astronauts for long-term space travel. Imagine stepping into a fully immersive environment where you can experience the conditions of space without leaving Earth. This technology allows future space travelers to familiarize themselves with spacecraft systems, conduct repairs, and practice essential skills in a simulated setting that closely mirrors the real experience. One of the primary uses of virtual reality is training for the psychological challenges of long-term missions. When astronauts are in space for extended periods, they encounter isolation, confinement, and the absence of natural light. A virtual reality environment can recreate various scenarios that replicate these stressors while equipping astronauts with coping mechanisms. They can learn how to manage conflict, maintain teamwork, and cultivate resilience through realistic simulations. Moreover, virtual reality can facilitate real-time collaboration among astronauts scattered across vast distances. By simulating shared environments, crew members can engage with one another as if they are working side by side. This strengthens communication and enhances the sense of community, which is vital for emotional well-being on a long journey. Testing equipment and systems is another critical aspect of preparing for space travel. Virtual reality can provide astronauts with complex machinery simulations, allowing them to practice troubleshooting and repairing vital systems without the high stakes associated with actual spacecraft. This kind of hands-on experience can significantly increase confidence and ensure that astronauts are well prepared for any situation they might face in space. Ultimately, virtual reality serves as a powerful tool to not only prepare astronauts for the technical demands of space travel, but also to bolster their mental and emotional preparedness for the challenges that come with long-term missions. By immersing them in these meticulously crafted virtual worlds, we can help ensure that they are ready for the extraordinary experiences that await them among the stars. The manipulation of gravity for travel is a fascinating concept that sparks imagination and scientific inquiry alike. If we could harness gravity, we might unlock the door to a new era of transportation, both within our planet and across the cosmos. One prominent idea is the concept of using gravitational fields for propulsion. Imagine a spacecraft that could create its own gravity field, allowing it to move effortlessly through space. This spacecraft would bend space around it, much like how a massive object, such as a planet, creates a dip in the fabric of space. If we could find a way to generate such fields, we might enable ourselves to travel vast distances in much shorter times. Another intriguing notion involves the use of antimatter. Antimatter is a substance composed of particles that have opposite charges to those in regular matter. When these two meet, they annihilate each other, releasing a tremendous amount of energy. If harnessed correctly, this energy could theoretically create a gravitational effect strong enough to propel a vehicle forward, providing a means of gravity-driven travel. We also have concepts rooted in Einstein's theory of relativity, suggesting manipulating the fabric of spacetime itself. Some theorists propose that advanced technology could warp or curve spacetime. This would allow for a sort of shortcut between 2 points in the universe, reducing travel time significantly. This idea leads to the imaginative concept of warp drives, which might allow for faster-than-light travel by altering our perception of distance. Lastly, there's speculation around advanced materials that might interact with gravity differently. Theories about negative mass or exotic materials could mean creating regions of spacetime with weaker gravitational forces. This could allow for unique travel methods, reducing the energy needed to escape a planet's gravity or even facilitating levitation. While these ideas exist largely in the realm of theoretical physics and science fiction, they present an exciting frontier for exploration. The possibility of manipulating gravity has the potential to change how we perceive distance, time, and travel itself. The journey to turn these concepts into reality is an endeavor filled with challenges, but the pursuit is one that continues to inspire scientists and dreamers around the world. Artificial intelligence is revolutionizing the field of astronomy in remarkable ways. Traditionally, astronomers would spend countless hours sifting through enormous amounts of data, whether from telescopes scanning the night sky or from simulations of cosmic events. Today, AI stands as a powerful ally in this process, significantly speeding up research and uncovering insights that might otherwise go unnoticed. One key area where AI excels is in image processing. Telescopes can capture vast quantities of images, often filled with noise or artifacts. AI algorithms can analyze these images faster and more accurately than human eyes alone. By learning to recognize patterns and anomalies, AI can help identify celestial objects, such as stars and galaxies, and even detect rare phenomena like supernovae. Another vital application is in analyzing large datasets from various sources, such as large-scale sky surveys. This data can contain millions of points related to different celestial events. AI can quickly categorize and classify these points, making it easier for astronomers to find specific events of interest, such as gravitational waves or the signatures of exoplanets orbiting distant stars. Furthermore, AI assists in predicting astronomical events. By examining historical data and patterns, it can help scientists forecast when rare events might occur, like asteroid approaches or solar flares. This predictive power enhances preparedness and safety, especially when dealing with events that could impact Earth. Moreover, AI is not just limited to analysis and monitoring, it's also involved in simulating cosmic events. By using AI in simulations, researchers can create complex models of galaxy formations or black hole dynamics, allowing for better understanding of the universe's evolution. Artificial intelligence is not just aiding astronomers, it's reshaping how they conduct research. This technology enhances efficiency, reveals hidden patterns in data, and drives new discoveries, ensuring that our understanding of the universe progresses at an unprecedented pace. The collaboration between human ingenuity and AI is opening new frontiers in astronomy that were once deemed impossible. Artificial intelligence is transforming how we navigate and control spacecraft in remarkable ways. One key application of AI is in autonomous navigation. Traditionally, spacecraft relied heavily on human input and pre-programmed commands. However, AI systems can analyze vast amounts of data from sensors and instruments in real time, allowing spacecraft to make decisions on their own. This is particularly useful for missions exploring distant planets, where communication delays between Earth and the spacecraft can be significant. Imagine a spacecraft on a mission to Mars deciding its own course when encountering unexpected obstacles rather than waiting for instructions from mission control. Another important function of AI in spacecraft is trajectory optimization. Using advanced algorithms, AI can calculate the most efficient path for a spacecraft, taking into account various factors like fuel consumption, gravitational influences from planets, and time constraints. This ensures that missions can be completed with minimal energy expenditure, maximizing the longevity of the spacecraft and expanding its operational capabilities. AI also plays a crucial role in monitoring spacecraft health. By continuously analyzing data from onboard systems, AI can detect anomalies or potential failures before they become critical issues. This predictive maintenance approach helps engineers address problems proactively, ensuring that the spacecraft remains operational throughout its mission. Moreover, AI assists in data processing and analysis. Space missions generate enormous amounts of information, from images of distant galaxies to readings from scientific instruments. AI can sift through this data efficiently, identifying patterns and extracting valuable insights quicker than human analysts could. This accelerates the research process, leading to faster discoveries in astrophysics and planetary science. Finally, AI enhances the human-machine interface, making control and monitoring of spacecraft easier for astronauts and mission operators. It can simplify complex tasks, provide intuitive recommendations, and even simulate various scenarios in training exercises. This collaboration between AI and human operators ensures that decision-making processes are both efficient and effective, ultimately leading to safer and more successful missions into the cosmos. Machine learning algorithms have become essential tools in the quest to find exoplanets or planets beyond our solar system. The sheer volume of data collected by space telescopes can be overwhelming, often consisting of thousands or even millions of observations of distant stars. This is where machine learning excels. It can analyze vast amounts of data quickly and identify patterns that would be nearly impossible for humans to discern. Imagine looking at thousands of stars, each twinkling in the night sky. Some stars might dim briefly as an exoplanet passes in front of them, creating a tiny shadow. A machine learning algorithm can be trained to recognize these slight changes in brightness. Through repeated learning, it becomes adept at finding these faint signals while filtering out noise from other sources, such as variations in star brightness due to natural fluctuations. The process begins by feeding the algorithm examples of known exoplanets, a kind of training data that helps it understand what a potential planet's signature looks like. As it analyzes new data, the algorithm can employ this knowledge to identify potential candidates. Moreover, machine learning can cluster similar patterns, making it easier for astronomers to prioritize which stars to study more closely. Beyond just finding exoplanets, these algorithms can also help determine their characteristics. By analyzing the light spectrum from a star when an exoplanet transits in front of it, machine learning can assess the composition of the planet's atmosphere. This can provide hints about the planet's habitability and other intriguing features. Through the efficiency and precision of machine learning, the search for exoplanets becomes more focused and productive, enabling scientists to expand our understanding of the universe and the potential for life beyond Earth. The collaboration between human intuition and artificial intelligence is paving the way for exciting discoveries in the vastness of space. Artificial intelligence is poised to transform manned space missions in a multitude of ways. Consider the vast distances and challenges astronauts face. Having AI as a companion can significantly enhance mission safety and efficiency. From the very beginning, AI can assist in planning and decision-making by analyzing vast amounts of data, predicting potential problems, and suggesting optimal solutions. Once astronauts are in space, AI systems can take on routine tasks, allowing crew members to focus on more critical aspects of their missions. Imagine an AI overseeing life support systems, monitoring oxygen levels and managing nutrition. It can alert astronauts to any anomalies before they become serious issues, ensuring safety in a challenging environment. Additionally, during long-duration missions, like a journey to Mars, manned crews can experience fatigue and stress. AI can help maintain mental well-being by providing companionship and support. It could engage astronauts in conversation or offer entertainment, reducing feelings of isolation far from Earth. Moreover, AI can facilitate complex scientific experiments. When strategically deployed, it can analyze data in real time, making adjustments to experiments as needed, which dramatically increases the potential for discovery. Moreover, if the need arises, an AI could operate equipment remotely, allowing astronauts to tackle multiple tasks simultaneously without being physically present. As we look further into the future, the integration of AI could extend to autonomous spacecraft. This means that, during a mission, AI could take over navigation and piloting duties, responding to unforeseen circumstances with precision and speed. In emergency situations, having AI ready to act could be a lifesaver, directing the crew on evacuation procedures or implementing emergency protocols without hesitation. The future of manned space missions is likely to be a collaborative effort between human intelligence and artificial intelligence. By offloading routine tasks, enhancing safety, providing companionship, and managing scientific work, AI has the potential to change how we explore the cosmos, making space travel more feasible and efficient than ever before. Artificial intelligence, or AI, plays a crucial role in analyzing the vast amounts of data collected by space telescopes. These telescopes gather images and information that can represent millions of celestial objects, from distant galaxies to nearby planets. Processing this data manually would take an enormous amount of time and skill, making AI an invaluable tool in this context. AI systems can quickly scan through images and data points, identifying patterns that would be difficult for humans to detect. Imagine trying to find a single needle in a haystack, where the haystack is the universe itself. AI algorithms can be trained to automatically recognize specific types of objects, such as stars, planets, or asteroids, making it much faster to categorize what is being observed. Furthermore, AI enhances the ability to analyze light signatures from these celestial bodies. Different elements emit and absorb light at unique wavelengths. AI can learn to identify these patterns, allowing scientists to uncover details about the composition and temperature of distant stars or the atmosphere of exoplanets. This not only speeds up the process, but also increases the accuracy of the findings. Moreover, AI can assist in predicting celestial events. By analyzing historical data, AI systems can spot trends and make forecasts about occurrences like supernova explosions or asteroid trajectories. These predictions can help astronomers prepare for future observations, potentially revealing new discoveries. Finally, machine learning, a subset of AI, allows these systems to improve over time. The more data they process, the more they learn. This ongoing refinement means that AI can adapt to new challenges, providing deeper insights into the mysteries of the universe. Overall, AI is transforming how we extract knowledge from the cosmos, amplifying our ability to explore and understand the universe more effectively than ever before. As space exploration evolves, the use of autonomous AI systems raises several ethical concerns that require careful consideration. First, there's the issue of decision-making authority. When machines are programmed to make decisions, especially in critical situations such as landing on another planet or managing resources in space, questions arise about accountability. Who is responsible if an autonomous system makes a mistake that leads to failure or harm? The lack of human oversight can complicate this issue, as it may be difficult to assign blame. Another concern is the impact on human roles in exploration. As AI takes on more responsibilities, will astronauts and scientists become too dependent on these systems? This reliance could erode essential skills needed for navigating unpredictable challenges in space. Additionally, we must consider the potential for biases encoded in the AI. If these systems learn from historic data or from human developers, they might carry forward biases that affect their operations, potentially leading to unintended consequences. The environmental ethics of other worlds also comes into play. Autonomous robots may inadvertently contaminate pristine ecosystems on other planets with Earth microorganisms. This raises questions about our responsibility to preserve these alien environments. Moreover, as nations and private companies race to explore space, concerns about the militarization of AI systems for security purposes arise. There's potential for autonomous systems to be weaponized, leading to a new dimension of conflict among nations in space. Lastly, there's the profound question of how these technologies impact our understanding of life and intelligence. If AI systems become highly advanced, should we consider their rights or welfare? As we push the boundaries of exploration, grappling with these ethical concerns is crucial to ensure that the pursuit of knowledge does not come at the cost of our values or the environments we explore. Engaging in this dialogue will help shape a responsible approach to using AI in one of humanity's most adventurous endeavors. Artificial intelligence has the potential to play a vital role in supporting human astronauts as they venture into space. Imagine a scenario where astronauts are far from Earth, perhaps on a mission to Mars or exploring the depths of the Moon. The challenges they face are immense, from dealing with life-supporting systems to conducting scientific research in an unpredictable environment. This is where AI comes in. Think of AI as an experienced co-pilot. While human astronauts possess creativity and problem-solving skills, AI can analyze vast amounts of data quickly and accurately. For instance, if astronauts encounter a technical issue with their spacecraft or life support systems, AI can process sensor data and identify the problem's root cause, all while suggesting possible solutions. This could significantly reduce the time needed to resolve critical issues, enhancing safety and mission success. AI tools can also assist in daily operations. Envision astronauts using voice commands to interact with AI that manages systems on the spacecraft. They could simply say, "Adjust the temperature," and the AI would make the necessary adjustments, allowing astronauts to focus more on their scientific tasks or maintenance activities rather than manual controls. Moreover, AI can function as a research assistant. Astronauts can gather scientific data, such as samples from other planets, and AI algorithms can analyze this information instantly. It can identify patterns and suggest further experiments or areas for exploration. This ensures that the limited time astronauts have on distant worlds is used effectively and purposefully. Additionally, AI can play a key role in health monitoring. Space missions can expose astronauts to radiation and other risks that might affect their physical well-being. AI systems can constantly analyze health data, alerting astronauts to any health concerns that may need attention before they become critical. AI serves as a powerful partner for human astronauts in space by enhancing problem-solving, managing operational tasks, assisting in scientific research, and monitoring health. This collaboration will not only make space missions more efficient, but also help safeguard the well-being of those brave enough to explore the final frontier. Science fiction has played a significant role in shaping real-world space exploration by inspiring visions of what is possible beyond Earth. From the early tales of space travel to modern cinematic adventures, these stories have sparked the imagination of scientists, engineers, and the public alike. They present ideas that often seem outlandish but can motivate serious scientific inquiry. Consider the concept of space travel itself. Classic novels and films showcased journeys to the moon and beyond, which encouraged early researchers to think more deeply about the mechanics of rocket propulsion and the possibilities of human existence in outer space. These imaginative works provided both a framework and a priming motivation for engineers to develop technologies that would eventually make moon landings and long-duration space missions a reality. Moreover, science fiction has introduced the public to advanced concepts like artificial intelligence, robotics, and terraforming. These ideas have pushed the boundaries of technology in real life, leading to innovations in robotic missions to Mars and other celestial bodies. The portrayal of advanced life forms and civilizations in distant galaxies has also increased interest in the search for extraterrestrial life, prompting scientific endeavors to explore planets and moons in our own solar system. Furthermore, science fiction often highlights important ethical and societal questions surrounding space exploration. such as the implications of colonizing other planets, the protection of extraterrestrial environments, and the responsibilities we have as explorers. These narratives encourage discussions in real life about the need for responsible stewardship of space. Ultimately, science fiction bridges the gap between fantastical ideas and scientific realities, instilling a sense of curiosity and ambition in humanity's quest to explore the cosmos. It compels us to dream bigger and fuels the next generation of scientists to take meaningful steps toward turning those dreams into tangible achievements. Throughout history, literature has served as a fertile ground for imaginative ideas that have inspired tangible technological advances. One notable example is the concept of the submarine, which was envisioned by Jules Verne in his novel 20,000 Leagues Under the Sea. He introduced Captain Nemo and his advanced underwater vessel, igniting the idea of exploring the oceans beneath the surface. This fictional technology paved the way for real developments in submarine engineering, making deep-sea exploration possible. Another visionary concept comes from Arthur C. Clarke's 2001: A Space Odyssey. In this narrative, Clarke introduced the idea of space stations and artificial intelligence, showcasing the potential for human presence in space. His vision influenced the design of real-life space stations and the development of sophisticated AI systems, reflecting how stories can inform actual methodologies in technology. Moreover, H.G. Wells imagined time travel in The Time Machine. While time travel remains a theoretical concept, Wells's creativity inspired scientists to explore the possibilities of time and space in ways they had not previously considered, engaging them in discussions that have led to advances in theoretical physics. The vision of virtual reality in works like Neuromancer by William Gibson also deserves mention. Gibson's narrative envisioned cyberspace as a digital landscape where individuals could interact, which spurred innovations in computer technology and the development of virtual reality systems, now a reality in gaming and training simulations. Literature captivates the imagination and challenges the status quo. These visionary ideas not only entertain, but also motivate scientists and technologists to turn fiction into reality. When we look at the advancements inspired by these stories, it becomes clear that creativity is a powerful catalyst for scientific progress. The way space is portrayed in films plays a crucial role in shaping public perception and interest in the universe beyond our planet. Movies often serve as a powerful medium that can spark imagination and wonder. When audiences see majestic visuals of distant galaxies, stunning nebulae, or thrilling space battles, they may feel curious and inspired to learn more about the real cosmos. For many, the escapism offered by these films transforms an abstract concept into something tangible and relatable. In popular movies, characters exploring new worlds or overcoming cosmic challenges allow viewers to empathize with their adventures. This human connection can transform the intimidating scale of space into an exciting quest, making science seem thrilling rather than daunting. Furthermore, films often introduce audiences to scientific ideas, sometimes even before they are widely understood. Concepts like black holes, wormholes, or the potential for extraterrestrial life become common topics of conversation after a blockbuster film is released. While filmmakers may take creative liberties, they often use real science as a foundation, encouraging viewers to delve deeper into what is scientifically accurate and what remains speculative. However, not all representations are beneficial. Some films may portray space inaccurately or sensationalize elements for entertainment. Such distortions can lead to misconceptions about space travel, gravity, or the nature of our universe. Despite this, films often ignite curiosity, prompting individuals to seek real information from books, documentaries, or scientific articles. Ultimately, the influence of space in cinema extends beyond mere entertainment. It shapes cultural narratives about exploration and discovery, urging society to consider what lies beyond our atmosphere and inspiring future generations to pursue careers in science, technology, and space exploration. Through this artistic lens, the vastness of space becomes not just a backdrop for drama, but a frontier that beckons us to explore its mysteries. Creative thinking plays a crucial role in overcoming the challenges of space exploration. The unknown nature of space presents numerous obstacles, often requiring innovative solutions that have never been tried before. When exploring beyond our planet, engineers and scientists may encounter difficulties that traditional methods cannot solve. This is where creativity becomes essential. For instance, when designing spacecraft, engineers must consider a wide range of factors, including harsh environments, limited resources, and the need for advanced technology.